Okay, so welcome back. So what we're going to do today is we're going to go through past paper questions on differentiation, specifically kind of the rule stuff. But you know how the study clicks documents come together. Sometimes they'll just pull in questions from like algebra and just like differentiation applications. So there'll be even some integration in this. So these PDFs never get compiled properly on study clicks. The way to do it, they're pretty lazy. So yeah, so that's I have obviously gone through the PDF here and I've kind of highlighted some of the questions that we, definitely need to know, and we'll be kind of going through them one by one. And it's relatively not that big of a PDF here, so 64 pages, so I'm hoping to get most of this done within the hour. So yeah, so we'll get straight into it, and then obviously when I'm getting a question set up, something like this here, once it's set up, so let me show you what it looked like when it's set up. So snip that. So when it's set up like this, I recommend kind of pausing the video and doing it yourself, and then kind of watch me do out the solution and see did you get the same. Okay, so that's definitely the way to get the most out of these videos. Okay, so yeah, so always be pausing the video before I kind of start working into them. Okay, so we've got this function here, bit of an unusual looking function, and we're asked to work out dy dx, straightforward enough stuff. So what we could probably do here is something like a quotient rule. So we're all hopefully familiar with the product and the quotient rules. Um, so the thing with the quote, let me have just a glance at them here because you'll see me doing this a few times in the video. Let me whip up our product. So our products and quotient rules, I'm sure we all know it. So there's an interesting thing you can do. So you can see the quotient rule is a bit more of a complicated formula. So there's a way you can always like use the product rule and never have to use the quotient rule. So I'll show you it here. So let's go back here. So what you can do is you can bring up the thing on the bottom. So you can rewrite this as y equals x squared. Now you can obviously just do a quotient rule as well, I'm sure people can do it, but I'm just showing people this. So that would be called e to the minus x when it comes up. And when it moves up, it leaves behind like a 1 on the bottom, so there's no need to kind of mention it. Why does it do that? So that's just a general rule. You'll see it a few times today. If you have like 1 over x on the bottom, that's x to the power 1. When it comes up, it'll have like a positive power. Okay, or the power changes sign. So if it was positive on the bottom, it comes up, it's negative. Um, so we should all be okay with that kind of idea. It's the same like if you had the number 2, you could write the number 2 because that's 2 to the 1 on top as 1 over 2 to the minus 1. Okay, so people are hopefully okay with that logic. And so the great thing about writing it this way now, I can just use a quotient rule, or sorry, a product rule on these two things here, where this can be the u and this can be the v. And so when you're doing this, just be neat for yourself and for the examiner. So say like u equals x squared minus x. Say v equals e to the minus x. And directly underneath that, say du dx is equal to 2x minus 1. And dv dx. So when we're differentiating these, the rule for this is to stay exactly the same. And then we multiply by the derivative of what's in the power. So what's the derivative of minus x? So it's minus 1. Okay, so that's that is, and what I like about doing it this way is the when we're subbing in here now, the formula for this is pretty straightforward. It's just like u dv dx, and then it's always a plus here, v du dx. Okay, but it's pretty easy to remember this rather that you won't have to go to look at the tables book. All you do is you basically just pick out whichever, because they were plus and it doesn't matter which order you add them in. So you can just like take this one, multiply it by the other guy's derivative, then add it to this one, multiplied by the other guy's derivative. So that way you don't need to kind of be picking up a tables book to kind of do it out. Okay, so let's just sub that in here. X squared minus x, this is the u, multiplied by the other guy's derivative, so that's minus e to the minus x, plus, and then it's a v, which is an e to the minus x. Good to have 4 brackets like I'm doing here. And then 2x minus 1. And it's a bit annoying here, so sometimes they say like don't simplify it out, but this one actually does want it simplified out, so let me hammer this out. So we get minus e to the minus x, x squared. Then we get a plus x e to the minus x. Then this gives a plus 2x kind of e to the minus x. So I should have written, I kept the order because I'm kind of putting the x's first sometimes and then the e to the x. So I should have been more consistent here, but it's fine. E to the minus x. So what kind of goes together here? So these two will add together because they're both x's. So you'll get something like And you could probably factor out an e to the minus x. So you take out an e to the minus x of everyone, and it'll leave behind x squared plus 3x and a minus 1. And that probably won't factorize anymore. But anyways, that's fine. Okay, cool. So we'll move on. We'll move on. Good few things to cover. So this is a really good one here. So get a derivative of this. So obviously pause the video, give it a go. So what you got to understand is where that 2 is located, okay? That 2 is actually, when it's located there, it actually means everything is being squared, okay? So the reason they kind of put the 2 in there is because they don't want it to look like this, and people are pretty lazy. They don't like to always write brackets, so they don't want it to look like that, because that kind of looks like it just belongs to the 2. The x belongs to just the x there, and that's a completely different thing. This is tan 5x squared. So when they write the 2 in there like that, it actually means this, okay? So they want the derivative of that, so always good to call it something. So let's call it y. Right, so how do we take a derivative of this? So we're going to use our chain rule here. So we write that we can just get dy dx straight away here. So what we do is, the rule for this is we multiply down by the power, okay? And we keep the inside the same, and then we reduce the power by 1. So we multiply down by the power, keeping the inside exactly the same, reduce the power by 1, so it goes down to 1, and then we put a dot here to say multiply. We multiply it by the derivative of what's on the inside. Now if you go and check your tables book, you'll see that the derivative of tan is sec. So again, what do we do here? But tan has something in it that's other than x, so it's 5x. So what we do is we keep the inside the same there. So what we write is sec squared 5x, keeping the 5x the same, and then we multiply by the derivative of what's inside this, which is a 5. So the way to think about that there, if that's confusing to people, is it's a bit like an onion. You're kind of, you do the outer peel in here first, right? Keeping the inside the same, and then you kind of peel through this layer, and then you finally get in here to take the derivative of that at the 5. So that's one way you could describe it. You're kind of peeling your way in, and every time you do it, you kind of keep the inside the same. So the inside was kept the same here, this 5x was kept the same, and then we multiply by the derivatives of the insides, like such. So if that's confusing, I recommend kind of practicing a few of them in the book, okay? You might see a few more of them as we move along. So then it's being annoying here again, so I have to simplify my answer, it says. So I probably would simplify this a bit anyways. I'll bring the 10 out, I'll call this a 5x, and then a sec squared 5x. And that'll do them. Simplified enough. Okay, right, yep, nothing else to say there. I think that's fine. Yeah, and you can find that the derivative of tan x is sec squared from your tables book. I probably should highlight that here rather than just telling you trust me. Oh, I've actually moved past it. I don't want the trigonometry thing, I want the differentiation. So when you're taking a derivative of tan x, it becomes sec squared x. And so when we were taking the derivative of tan 5x, we had to kind of keep the inside the same and then multiply by the derivative of the inside afterwards, which is what I done. Okay, so easy one here. So, but again, these are stuff you should know, so I'm doing them just in case people don't know them. So this is nice. They say don't simplify your answer. That's great. We love to see that. Okay. Yeah, so just work out f dash x, easy stuff. So f dash x, what we do is we multiply down by the power, keep the inside the exact same, reduce the power by 1, becomes a 27. Then we go and we multiply by the derivative of what was inside. And the derivative of what was inside here will be a 15x to the 4. Okay, because the derivative of this, you multiply down by the power, becomes 15, and then it becomes x to the 4. The derivative of the minus 4 is 0, because it's a constant. And so that's that. And then it says just don't simplify it, and I'm okay with that. Okay, cool. Keep moving along. So what are we doing? We haven't even hit 10 minutes. That's great. Good going. So yes, nice question here on a kind of an exponential function that has it actually means something. So it's to do with a drug in someone's system. And so they ask a few different questions on this. So let's see if I can kind of yeah, that looks good. So I'll be able to bring the question along with us as we work through it. So some of this will be algebra. I think the differentiation part comes afterwards, but this is pretty good. This is kind of how it comes up in state exams. So I'll go through it. Okay, so pause the video, give those first two parts a go, of course. It asks what was the concentration of the drug in the patient's blood immediately following the initial dose. So as we can see, this models the concentration in milligrams per liter in the person's blood after a certain time t. So if you want to get the initial dose, t equals 0. Okay, there's a great amount of repetition in these kind of questions for this sort of thing. So you could call it z of 0 here, like this. And then you go 4, e, and then it's really e to the 0. E to the power of 0, everyone should know, is anything to the power of 0 is 1, so then that just works out as 4. Now this thing has units, you got to be careful here. You were told it has units of mg, milligrams per liter, so you'd actually lose marks if you didn't write that down, okay? It has units, so read your question carefully. What is the concentration at 11:30 a.m.? Well, if this is, and t is in probably in hours, is it? It is, yeah. So how many hours pass between this? So it's 2.5 hours. So you just kind of go C of 2.5 here. C of 2.5, and then you go 4E minus 0.05 bracket 2.5. Type that into your calculator to one decimal place. I'll do it here, just in case anyone done this out, you know, and they're looking for an answer. Minus 0.05 multiplied by 2.5. So that's working out as 3.53. And then to the nearest, I would say it's 3.5. And again, it has units, mg per liter. Okay. What else? Other comments? Yeah, so I never actually spoke about the function. So what do we notice there? After 2.5 hours, the concentration dropped because initially it was at 4. So we should all know from our basic functions that this is exponential decay is what this function is. So if you're to draw a graph of this, what it would be is it's an exponential function that's decaying like this, okay, down to 0. Where does it go through on the y-axis? It goes through 4, and we know that because that's when we set t to 0, we find where it crosses the y-axis, so it's that number in front. And yeah, so you can see it's decaying down here because we found after 2.5 hours it had a value of something like, what was it, 3.5 there a second ago? Okay, so that's great. So then find the rate of change. This is what we're interested in. Find the rate of change at 1 p.m. Okay, so we take a derivative of that function up there. So let me scroll on down here, and then I have this set up like this. Fantastic. Okay, so obviously pause the video, give them a go. Right, so let's take a derivative of, and we'll call it c dash t. So the way the 4 here doesn't do anything, the 4 is just multiplying the answer, so the 4 will just be there chilling out, it's not doing anything. So the derivatives of this thing here, when we're taking derivatives of exponentials, the way you got to remember that is they stay exactly the same, and then you multiply by the derivative of the power. That's how we take a derivative of exponentials like that. So we go 4 does nothing. Okay, it's just there, it'll be there. And then, as I said, this thing stays exactly the same. And then we just multiply by the derivative of the power. And then the derivative of power there is this. Okay. Yeah, so that's it. And we were told to get this at 1 p.m. and this is 9 a.m. that t starts, so t really is equal to 4 here in this question. So we really want c dash 4. And then that's 4e to the minus 0.05 bracket 4, and then the whole thing then is multiplied by minus 0.05. And then we'll talk about the units afterwards. So let me type that into my calculator. 4 by e minus 0.05 by 4, and then the whole thing multiplied by. Great, so I get this number of minus, so it's a minus, and we'll explain why it's a minus after. Did you say number of decimal places? It didn't. In a state exam, it probably would say the number of decimal places, but we'll call it 164, okay? Now, what would the units of that be? So, C was in milligrams per liter, and we're just after getting what this thing is here. This thing is like dc dt. Okay, it's the rate of change of C with respect to time. So what this is, the units of this will be the units of whatever C was divided by the units of dt, which is in hours. So this guy has units of milligrams per liter. I'll write it like that. And you could just write over hours. Okay. Yeah, how did this spell hours up here? Yes, they spell it out. Okay, so what does it mean? Okay, so you're asked to, what does it represent? So what you're kind of looking at here is when the time is 1 p.m., the patient is losing, right? It's reducing in their blood because it's a negative sign. The concentration of the drug is reducing by 0.164 milligrams per liter for every hour that passes. Okay, so at that moment of time. So what happens is the rate of change itself changes with time. So look at this here. You can see the rate. This is the rate of change formula for any given time, and you can see it depends on T. So this isn't a constant. It's not, the person's blood is not, the concentration of the drug is not always reducing at this rate. This rate changes depending on what time you put in. Okay, so at 1 p.m., this is the rate of change of the concentration of drug in their blood per hour. Okay, yeah, hopefully people are happy with that. And then kind of an algebra question now to finish it off down here. What is the latest time the patient can receive another dose of the drug? So they said things get bad when it's 2.5 here. So you go 2.5 equals 4 e to the minus 0.05 t. This is one equation, one unknown. So you should all know how to solve this equation. Particularly t is in the power now, so you should know you're going to need logs. So you kind of bring the 4 over, and you got 2.5 over 4 equals e to the minus 0.05 t. You can then apply logs. So there's a quick way to just turn this into logs without needing your tables book. Who's the base here? E is the base. So, and the whole point of using logs is to get the power on its own. So who's going to be on their own? So the minus 0.05t will be on its own. Then the log has two positions. It's got a position down here and a position up here. So as I said, the base is E, and the great thing is the base stays the base. And so then that just leaves position for the other thing here, the 2.5 over 4. So hopefully that makes sense. The whole point of logs is to get the power on its own, so that tells you that goes there. The base stays the base, and then that leaves one slot for this thing. So then t, so we call log e as well ln, so it's nice to not be subbing things into a calculator too early here. You can actually just write this like this, and then the whole thing over minus 0.05. So the examiner would like that, for you to write it like that. So ln 2.5 over 4 divided by minus 0.05, and now I'm getting t is 9.4 hours, right? And then it's probably being annoying here. It says the latest time, so whatever 9.4 hours is on top of 9 a.m. So it's like whatever 6 p.m. 6 p.m. and 0.4 of an hour is 24 minutes, is it? So it's like probably like 6 p.m. and 24 in p.m. Okay, so that'll be an 18 then. Yeah, I'm sure everyone can add 9.4 hours to 9 a.m. Okay, so foundation math stuff. Okay, so right, let's move along. Another one here. So this is a nice question. This is like a trigonometry thing. So we'll kind of do the differentiation part of this, and then there's a really important part of it, which I've just kind of circled, and that's a kind of hint. If you don't know how to do it, you're to go and look at the trigonometry important past paper question video I put on the channel. Great, so you can have a read of that there. Pause the video and have a read of it to understand what's going on in the question. So the idea is there's just this observation wheel, and there's a dot that kind of moves from A to B because it spins anti-clockwise here. And you're told some details about how it rotates, full rotation every 30 minutes. So that kind of gives away its period. And then point A is 15 meters from the ground here, and the wheel has a radius of 60. Okay, so that tells us it probably goes from here, if that then a radius of 60, so B then is like a height of 75, that kind of thing. Okay, so we're asked to show this down here, so I will do this with us. So obviously pause the video, see can you come up with how to do this, how you get these values. So the idea is the range of this function here, because we're tracking this point, its minimum value is 15 and its maximum value up here. Its maximum value is, because this is 60 to here, so you just add 120, 60, 60 and 15. So 135 up to there, okay? Now the midway line, the midway point here will be 75, okay? And that is this value here, okay? So as we would have done if you've watched the trig, if this doesn't make sense, you have to go and watch those trigonometry videos I have on the channel. Okay, this is super important if you're in leaving cert higher level maths. You know, you expect this kind of thing. So that value that we put there is always the midway point, right? Now, so then the reason there's a 60 here is because that's to do with the amplitude, how high above and how low below the 75 we go, and that's 60 because of the radius of the wheel. And then, yeah, so they say that this function's a minus cos, so they just gave us that, which is nice because that would be a bit trickier to work out. But again, that's all covered in those trigonometry videos for people who don't understand this. So to get b, there's a pretty important formula for b. B is always equal to the period over 2 pi. I think that's the correct way I've written that. Is it 2, or is it 2 pi? Let me think now. I think that's the formula. One sec. Yeah, no, that's the other way around. I knew there was something funny about it. So that's just me kind of rushing things. So the formula for b is 2 pi over period. Okay. So, and anyways, we were told to show something here, so you can confirm if it's right or not. So what's the period here? So again, it says t, you got to be careful. It says t is in minutes, right? So, and then it says a full rotation happens in 30 minutes. So then the period in minutes is 30. So you just sub that in there for a period. So 2 pi over 30, and then 2's cancel, and you get a 15 on the bottom. And there you go. Right, so that's important. That's kind of trigonometry stuff. I've done loads of them. If you go and watch those trigonometry videos, show that the time taken for the pod to go from A to B is 7.5 minutes. Well, that's easy. That people should know if it takes 30 minutes to do a full rotation. Okay, A to B is a quarter rotation, so you know 7.5 minutes is a quarter rotation. I wouldn't show any more work because it's such a stupidly simple question, you know. Okay. Sound. Now, average height. So this here is actually an integration question. Okay, so this isn't differentiation, but I'm going to do it because this is really really important. Okay, that you're able to do this kind of thing. So let me get the function. I'll write the function what it was here. So it was the function is h of t is equal to 75 minus 60 cosine pi t over 15, right? So we need that for our calculations later. Okay. So let's put that there at the top. Okay, so just discussing this now. So that's a buzzword if ever you see it in the exam, the word average. Okay, there's a form. Anytime you can go through past papers and you'll notice that this word average, it's a kind of buzzword to use this average value formula. So we should all know this from our integration chapter if we don't it. Our average value formula for a function is equal to 1 over b minus a integral from a to b of the function with respect to x. Okay, really really important formula that you know that. So anytime you kind of see this word average, it's kind of a good hint. Average height means average value is to use this formula. So then let's do this. So it wants it as it travels from point A to point B. So in this question here, we're going to be they're going to be times. So that's kind of why this is a part 2. And before we were shown that I think the wheel starts at A. Just checking here, and we can check this. If you put 0 in, cosine of 0, the cosine of 0 we should all know is 1, and so then we get 75 minus 60 times 1. So yeah, the problem starts when the wheel is at A. Okay, cool. So then what this is doing here, if I'm correct in this, what we're really integrating here, let me get a good color for this. So this is equal to 1 over the time it takes to get up to B. So 7.5 minus the time it was at A. And then we're integrating from t value of 0 to 7.5 of our function up here, which is 75 minus 60. Let me move this out of the way. Minus 60 cosine pi t over 15, and all of that is respect to dt. Okay. So yeah, we're just integrating the function with respect to t between the 2 points of interest that we want to get the average value between a and b. Okay. So yeah, I'm happy with that. So basically, I got to integrate that now. So let me make a room for this. I can probably delete this here now because I've already stated the formula t, and I want some room for my calculation. So obviously, if good to, we call this AV for average value. Um, good to have a go at doing this yourself. Okay, so this thing is ready to integrate, so I can just replace this with a 1 over 7.5. Okay, I can change this to a straight line because I'm going to do in the integration now. Now the integral of 75 is 75t. Now the integral of cos, what does cos become? It becomes plus sign when you integrate it. So that would be minus 60, and then it doesn't change sign because we go back to a plus sign over 15. And then we divide by the number that was multiplying uh, the t. So then this would multiply by 15 over pi. So a tricky little integration there for anyone who's struggling with that. So then what we do is we go and we put in the limits. So again, we got to be neat for the examiner doing this. So this is average value. So we got a 1 over 7.5, and I'm going to use a big square bracket here. And then there's going to be 2 mini square brackets in here. The first square bracket, we'll be putting the upper limit in here. So we'll be going 75 multiplied by 7.5. Take away 60. I can just write 60 sign. Pi times 7, because the examiner wants to see you subbing in, so you do need to have all this. And then big bracket around that times 15 over pi. Close that up. So that's the first square bracket inside the big square bracket. And then we got to take away from this another square bracket when we put the lower limit in. Now this is pretty easy. We're putting 0 in here. So it'll be 75 times 0, which is 0. Now we should all know what sine of 0 is. Sine of 0 is 0. So then it's also a minus 0 here. Okay. So hopefully people are good with that. Yeah, so then I just got to type this into a calculator. So let me pause the video and multiply all this out, and we get the average value. And it'll probably be in meters because I imagine the function was in meters above. I think it was. Oh, just another big point, make sure your calculator is in radians, of course, because this question's in radians. Okay, I typed that into the calculator, so I got 36.8 meters. And that should make rough sense to people because when you're going from remember A was at like 15 meters and B was at, I think it was something like 75 meters. So yeah, you can see why it might have a value between 15 and 75 meters as the average value. Just another thing, if you were asked this question to give your answer in terms of pi, but this question was already pretty hard, so they wouldn't have made you do this. You could have just multiplied this in. The 7.5 would have cancelled with this, so you'd have got the number 75 there. This 75 could cancel, say, with this 15 and just leave a 2 here. So then you'd have 2 times the 160, so that's minus 120. So if you're asked to leave this in terms of pi, you would get AV equals 75 and then minus 120 over pi, because you got 2 over pi times your 60. And everyone should know that the 7.5 over 15 is a half, and we should know that the sine of pi over 2 is 1. So then there's your 1. So you could leave your answer 75 minus 120 over pi. And let me type that in here and make sure I get the same number as I got there. I do. I get 36.8. So fantastic. Great. So that's a good question there. Obviously, if there's parts of that didn't make sense, it tells you now what you kind of need to go and revise. So here they make people graph the function. I've done loads of that there when I was doing the the trigonometry videos. So you can go back and look at the graphs of stuff. I think there's a question here. I'll just get people to kind of read this here and make sure you know how to solve this question. If you don't, go back and look at my important past paper questions you should know on trigonometry, and you'll see lots of examples of how to solve this where you'll be able to get the 2 values for t, because these function a bit like a quadratic. They always have 2 values of t. Okay. So this is a really important buzzword for us here. So this is different to what we had above there. So they want the average rate of change. Okay, so we've got to understand that when we get dy dx, right? This is what's known as the instantaneous rate of change, right? And we should remember our slope formula from junior cert and also still even cert, where we get y2 minus y1 over x2 minus x1. So we know that's the slope, but the slope is actually the average rate of change between 2 points. So, okay, so it's the average rate of change. And if you don't know this, go have a look back at the book and you'll confirm this. So it's the average rate of change, and so it's kind of between 2 points. Okay, so to get an average rate of change, you need 2 points. Whereas an instantaneous rate of change, this should be a hint. If it's instantaneous, it means it's at one instant. So that's kind of like at 1 point. Okay. So it wants the average rate of change of the height of the pod as that goes from A to B. So one way of doing that is to take our derivative of our function, or sorry, no, you just get the height of it at A and the height of it at B, and then take away the time. So you just use the slope formula here. So m equals as it goes from A to B. So if we label A as a point on that graph from before, uh, A was I think 15 meters, and that happened when t was 0, and then B was 75 meters, and that happened when t was 7.5. So what we're doing there is we're kind of putting h and t, because remember the y here is height and the x is t. Okay, and so we'll use our slope formula here. We'll label these up. You go x1, y1, x2, y2, and so m here. Let me try and move it down. I don't want it to be too messy. Don't want people to blow up. We go yeah, so I've obviously written the x's in here, so I wrote 15 in for x there, so x is t, so I've then the other way around, sorry. So x, look what's on the x-axis, it's time. So this here is time, and then this here is height. So then in for x here, this is the point A, and this is the point B. So in for x at 0 time, you're 15 meters off the ground. At 7.5 minutes, you're 75 meters off the ground. So then the slope is, which will be the average rate of change, is 75 minus 15 over x2 minus x1, so that's 7.5 minus 0. And so that works out as basically 60 divided by 7.5. So it's an answer of 8. What would the units of that be? So think of the units. It would have the units of y's units divided by t's units. So it's basically h was in meters and this was in minutes. So then this is meters per minute. So on average, as you move from A to B, and this is a plus, notice this is a plus, the height of the observer increases by 8 meters per minute on average, okay? But their instantaneous rate of change won't be constant. It'll be changing every moment, the instantaneous rate of change, but the average between 2 points will work out like a constant like this. So that's just me doing a question there. I obviously don't have, I'm going through loads of questions here. I don't have time to explain this too much more, but if this is confusing, this is a hint to go and have a look at the book and revise instantaneous rates of change and average rates of change, and why the slope formula is used for the average rates of change, and how you can just take 2 points like A and B, label them up here, and calculate a thing. Okay, cool. And yeah, go, if you don't know how to solve that question and get those 2 times, go look at my trigonometry videos. Great. So our next question here that I have a mark beside is this one, where Fia puts the money in. So I think this is just, it's standalone, yeah. So we'll just do this question here. Right, so Fia puts money in a savings account and leaves it there for a number of years. Okay, so if you watch the financial math tutorial videos, you can see how like our future values can be written this way in terms of an exponential. This is exponential growth because the power there is positive, so it goes up like that. Okay. Um, Use differentiation to find the rate at which the amount of money in the account is increasing after 3.5 years. So let's do this. So we just take our f dash t. The 5,000 does nothing. It's just a number multiplying things. When you take derivatives of exponentials like this, they stay exactly the same. And then you multiply by the derivative of the power, which is 0.04. And that's f dash t. So you see f dash t is not constant. This is the instantaneous rate of change, what I was talking about before. So it depends on what you give it as a time. So they say um, do it for 3.5 years because t is in years. You got to confirm that. Yep. Okay, so 5,000 e 0.04 04 times 3.5 times 0.04. Let's type that into a calculator and obviously have a good think about it. It has units, so if you haven't written units down for your answer, I recommend having a think about it because you'd lose marks if you didn't write down a unit for this question. 0.04. So I'm getting 230. And does it say rounded to the nearest euro? It does. So I'm getting 230.05. So as I've been kind of teaching people in good habits, you want to first of all write down a number like that, but then round it afterwards to the way they want it. Now they let you off here. They've actually told you the units. So the units are indeed euros per year. Okay, so that and it's positive as well. So that means the money in the account is increasing on basically by 230 euros per year at this moment in time. Okay, that's what it looks like it's going to increase, but that's what it looks like at a given instant. So this isn't like the average between like 2 points. Okay, so hopefully that makes sense to people. Any other comments there? Yeah, if you didn't know how to work out the units here, you just think about, well, what is f dash t? It's df over dt. What are the units of f? F is in euros. What are the units of t? T is in years, and so the units are f dash t are the same units as df dt, which is euros per year. Great. So let's move along. Yeah, we have a first principles one coming up later. Okay, so a nice one here. So it's a pretty basic sort of quotient rule kind of thing, isn't it? But I'm going to do that kind of my other express way. So I can use a product rule on this if I do this. So this is very, as I said, I'm sure people can use the quotient rule, so I might as well show you something else that's kind of cool in case you weren't showing up when you were being taught this in school. So you can just bring the thing on the bottom up and call it to the power of -1, and then you just make a product rule out of this, where this is like your u and this is your v. Okay. So then just kind of tell the examiner u is 6x plus 1, v is x to the 4 plus 3, power of -1. So then underneath this, beneath, du dx is equal to 6. Now dv dx, you multiply down by the power, keep the inside the exact same, because this is the chain rule, reduce the power by 1, you go down to that, and then you multiply by the derivative of the thing on the inside, which gives 4x cubed, because the 3 has no derivative, it's just it's because it's constant. Okay, and then you sub them into the product rule thing, and that's equal to dy dx. So you have to make sure you state what they're equal to. Okay, dy dx equals, we go u. So again, you don't need to look at the tables book for this. The quotient rule is a little bit more complicated. You do kind of need to make sure you put the minuses and the v's and the u's in the correct order kind of thing. So you just take one of them and you multiply it by the other guy's derivative. This is a bit messy here. So look at the way I write this. Okay, people should be okay with this. So that's a minus. Let me get it a little smaller. Minus over x to the 4 plus 3 squared. Okay, so think about that. That there is dv dx. What did I do? Because this is the power of -2, I can just bring it underneath and call it to the power of +2. Okay, in the same way I was able to bring the bottom up here, which is to the power of a +1, I bring it up and then it's to the power of -1. So So you just bring them up and down, you know. So it looks neater this way, you know. Right, and then a plus, and then it's V, so it's this guy, and then I can just write him now in his other format. Bring him underneath now to the power of 1, and then multiply that by du dx, which is 6. And then obviously we could just write the 6 up here, it's neater. Okay, so that's dy dx, and then it said get the value when x is -2, and they explicitly tell you what this means. It means just put -2 in for x. So let's do that. Let's put a thing in. I ran out of room, but I'd write this underneath. But you just want to show for the examiner this +1 bracket -4 times -2 to the 3 over, because you pick up a ton of marks like the calculator. Subbing this into the calculator actually doesn't pick up as much marks as you writing it down neatly on the page like this. Squared, close off the bracket, plus 6 over -2 to the 4 plus 3. So that actually is the answer there in orange, you know, and I'd get like whatever, maybe like 9 out of 10 marks for that. And then I get like maybe a bonus mark now for showing the examiner I can use a calculator properly. So I'll pause the video and get a number. Yeah, so I typed that in there and I got something like, you know, -238 over 361, and I'd leave it like that. I wouldn't go like turning it into a decimal, leave it as a fraction like that. And that's given I've typed it in correctly. As I said, it actually doesn't really matter that much if you know you get the right numerical answer here. What matters more is the workings, and then you actually show and you subbing into your workings. Okay, that's where all the marks are. A correct value at the end in a question like this isn't actually worth as much as this thing here in orange, you know. Because you know you're not going to penalize a student really heavily for like mistyping something into a calculator. Anyways, I'm happy with that. I'm moving on. Okay, so what are we on now? 41 minutes for the video. Okay, we're moving along. There's a few very interesting questions coming up. Oh, so we've got a nice one here, a bit of a trigonometric thing here. So find dy dx. Pause the video, give that a go. So yeah, we're going to use a product rule here. And we're going to go u is x, v is cos 2x. So du dx is going to be the number 1. dv dx. Now the differential of cos is minus sine, right? The inside stays the exact same, and then we go and we multiply by the derivative of the inside, which is 2. So this is what's inside here is 2x. So we kind of take, it's like the onion, we do the outside first, cos becomes minus sine by a derivative, keep the inside the same, and then multiply by the derivative of the inside. Great, and you sub those into your product rule, which as I said, you don't really need to go to tables book to remember, you just think it's basically take one of them that's undifferentiated, multiply it by the other guy differentiated. So it's really just u here, multiplied by this guy, which is a -2 sine 2x, plus v multiplied by du dx, which is 1, you know, it's 1. Okay. Yeah, so basically I would tidy that up here. It only takes a second. You'd go -2x sine 2x plus cos 2x. Happy days. Okay. If only they were all that quick. So this is an important one here now. So this is, I've put 3 marks beside this. This kind of question can come up and people really struggle with it. So we actually need our answer from just a second ago. Okay, so I need this to solve this question. And this is the format, this is how it always comes up. So we need to know, and not have forgotten, that dy dx is equal to this thing here. Now, you cannot integrate this thing, okay? There is no, for you doing your leaving cert maths, there is no such thing as a product rule for integration, okay? There are rules, like there's things called integration by parts and stuff, but that's not on the leaving cert maths course. Okay, so for you, when you look at something like this, you got to understand that you cannot integrate that. It just doesn't work, okay? You don't know how to do that. So to be able to do a question like this, they get you first to get a derivative and then somehow come up with a smart way of using your answer from that to work out a way to take an integral of this, even though you can't take an integral of it using your maths knowledge. So let's explain how this works. So let me get a neat way of doing this. I want to maybe take a snip of this. I'll have it in the center of the screen because I want a good bit of white area here to do this neatly. Okay, so this is the proper workings for this, okay? What you do is you actually this is the proper way to do this now. You multiply across by the dx. So for people who didn't know you could do this, you actually can. Okay, so this is mind-blowing for people if they don't know this. So you can actually multiply across by the dx. And what you can do is this, you can integrate both sides, okay? So you can just integrate both sides like this, right? And you're allowed to do this, you know, you're doing the same thing to both sides, so you're allowed to do it. I multiplied both sides here by dx. So that's why the dx landed over there, you know? Okay. So again, this was taught in the textbook, and so if you haven't seen this, I recommend go and practice a few of these in the textbook. But I suppose that's why you're here for a video like this, to kind of remind you of the things you should know. Hence the title of the video. Okay, so what we all need to know is the integral of dy becomes a full y, right? So then this is equal to the integral of this thing. So there's two parts of this thing, so you can actually just break it into the two parts. So the first part is we're trying to integrate minus 2x sine 2x with respect to dx. You see how dx is multiplying both of these, so you can multiply the dx in. And then it's plus the integral of this guy, integral of cos 2x dx. Now you're like, why on earth? What is he doing here? So think about this. The whole question I've been asked is to get the value of this thing. But I have it here, so I just need to move everyone away from it. Hopefully that makes sense to people. So when I move everyone away from this blue thing, right? It's the integral of minus 2x sine 2x dx. It's equal to y subtract the integral of cos 2x dx. Okay? And you're like, okay, but what is y? But sure, we knew what y was from before. Let me remind everyone of what y actually was. This is what y was. Y was equal to x cos 2x. And not forgetting that y was equal to x cos 2x. And what are we doing here? We're trying to get the integral of this. Oh, and as well too, this question has limits. So you can mention the limits now, is probably a good time to. So they go from 0 to pi over 2. And so if you put limits there, you put limits on this other guy. Pi over 2. And so look, this is our answer. This is, we just done some smart algebra stuff there to get our answer on our own. So our answer is basically whatever this orange thing in the squiggles is equal to. And we can just work this out. So let me try and get some room for this because it's pretty important. So let's make you smaller and put you up here out of the way. And then there's that important step of integrating. Of course, someone's gone missing. The pi here has gone run away. Pi over 2. And then we'll move this up like such. So then the thing we're looking for, pi over 2 integrated from 0 minus 2x sine 2x dx, the thing we're looking for in black, is actually equal to y. We can just sub in what y is. Y is x cos 2x. And then and as well too, yeah, so this thing is going to have limits. We have to put in the limits of between 0 and pi over 2. We'll talk about that in a second. And then this is, because this should give a value, you know. And then this is minus. So we can take an integral of this. We can switch to a straight line here. So we should know what the integral of cos 2x is. The integral of cos 2x, cos when it gets integrated goes back to a plus sign. Okay. So, and as well too, I have a minus here. That's probably a bit too high. I want to have that minus down here in the middle. The integral of cos goes back to a plus sign. And then instead of multiply, because this is integration, instead of multiplying by 2, we divide by 2. So people should be okay with that somewhat. And so that's it. So basically we just sub in our values here. So I'm really out of room here for this. So I'm just going to say that this equals, so this is the next part over here. I'd normally drop down and do it underneath. So this equals, you kind of put in square brackets. So we have putting pi over 2 in here. So this is pi over 2 cos pi. because pi over 2 times 2 is pi. Uh, close off that square bracket, and then it's minus this same thing here when you put the 0 in. When you put 0 in there, it'll just be 0. Okay, and then close off that square bracket, and then it's a minus, so we're doing this bracket over here, so it's another big square bracket. So we put the upper limit in. When you put the upper limit in there, you'll get sine pi, and then that's all over 2. There should be a square bracket there, and then that's minus when you put the lower limit in. And oh, I think, yeah, no. So the reason there's a 0 there, okay, the reason there's a 0 there is because this is 0 times cos 2 times 0. Just so you know, cos of 2 times 0 is actually 1, but because there's an x here, it's 0 times 1. But when you put 0 in for sine here, the thing just becomes 0, okay? So that's just a thing to watch out for. So yeah. So again, if this was a little bit complicated for people, oh yeah, you should know as well too, the value of cos pi. Cos pi is minus 1, so that will be minus pi over 2, because it's pi over 2 times minus 1. And then this is take away whatever sine pi is. Sine pi is 0, so really this is minus 0. So I'm getting minus pi over 2 for this answer. So there was a lot of work in there. Just let me check if that's correct. Yeah, that is correct. So yeah, so I may you definitely want to you want to practice a few of these in the textbook. If this was super confusing, you want to make some flashcards on it then. So particularly how we begin from our derivative here, we multiply across by the dx, we integrate both sides, and we get that y is equal to something with the thing we're actually looking for here in black. We move everyone away from the thing we're looking for, and then we get something like this in the squiggle box, and then the process follows something like this here. You sub in for the y, and then you do your integrations and you put in your limits. Okay, a little bit of a tough question. They don't get asked all that often, but they are absolutely fair game. That's why they come up in mocks a bit more than they do in the state exams, but that is fair game in a state exam as well. Okay, so we'll scroll on along. Scrolling down. I could probably zoom out a bit here. Okay, oh yeah, nice one. So this actually isn't differentiation, but it was obviously study clicks at their usual stupidity, putting a kind of limits question in here on a differentiation thing. So, but it was such a good question that I said I want people to do it. So have a go at doing this. Pause the video, give it a go. Okay, so hopefully you had a go with that. So when you're trying to evaluate limits like this, you always just try and put the limit in. So if we put infinity in at the minute, we'll get like infinity on top over the square root of like basically infinity minus 1, which is still infinity. Square root of infinity is still infinity. So you're getting this, and that is not equal to 1, okay? This thing is just what we call undefined, okay? So basically, that's not the way to solve this question. So the trick to this is you want to divide above and below by the highest power of n. So there's an n on top here, but you think there's an n squared here, right? But it's really, when you kind of take the square root, it's really like now you can't just take a square root of that because there's a minus 1 here, you know. So the trick to this is you've got to divide above and below by something, and the thing to divide above and below by is n. Okay, so I'll show two ways to kind of do this. So we're just going to focus on this thing here. We're going to do algebra tricks to it. So if I divide the top by n, there'll be an n here on the bottom. And then this is all over, big long divide line, over the square root 5n squared minus. So this is a tough question. That's why I picked it up. Okay, now just so you understand, this is the exact same as the thing up here. What did I do above and below? I divided above and below by n. And so I haven't broken the thing. It's still completely valid. Now, what you've got to realize here is we want this to be able to enter the square root here. So there are ways you can enter a square root. So how could a 9, for example, enter the square root of x? How can the 9 get in here? Well, you got to think what you can write 9 as. You can write 9 as the square root of 81. And then it can enter, because when two things, there's a rule in your tables book that root a times root b is root ab. So this is a really important algebra trick. So this is how you get the 9 to enter the square root. You change it to whatever it is as a square root itself, and then it can just go in. Okay, same thing here for your n. What is n? We could write n as the square root of n squared. Think about that. If you take the square root of n squared, you get n. So I'm running out of room here, but what I would do is I would replace that with the square root of n squared. Okay? And now because both of them are the square roots, there's this rule also. If you have root a over root b, they can enter into one another like this. Okay? So what this actually becomes, again, I'm saving room for myself here, but like if this was, I would be showing this would have been a new line, and then what I'm doing here now would also have been a brand new calculation. So basically that n squared can enter into this guy's square root, and they can all be just one big square root, like such. And now this is great because this n squared now will cancel with that there. So I'm going to write this now. So this all becomes equals, so you'd want to be a bit neater with your calculations on the page here. You get a 1 on top because that's what n over n is. And then this is over the square root of, you divide n squared into each of these, you'll get the number 5 there. And then it's minus 1 over n squared. Because you just separate the single fraction into two separate fractions. And now what you can do is you can actually get the limit of this. So you can go limit as n tends to infinity of 1 over the square root of 5 minus 1 over n squared. And you can just put infinity in here and it'll work out as 1 over the square root of 5 minus 1 over infinity. 1 over infinity is 0. If you don't know that, go back and look at the book for limits to know that. 1 over infinity is 0. So then this is really just 1 over the square root of 5 minus 0. And so the answer is 1 over root 5. Okay. So that's a good question. That's why I gave, a couple of minutes to that there. Another way students could have done that is, I think this is harder to see, is you could have factored out an n squared here. It's a little bit not so obvious. So you could have like taken out an n squared here. It would have left behind a 5 over a 1n squared. And then what you could have done is you could have said that, okay, you can split this up into the square root of n squared and the square root of, so that's like doing the rule in reverse. In the same way you can have root AB, you can then write it as two separate square roots like I done here. And so then what does that become? That becomes n over n, because square root of n squared is n, and then you get the root of 5 minus 1 over n squared, and the n's cancel, and then you're just left with 1 over the square root of 5 minus 1 over n squared. So the same factorizing we got before, and then you can put the limit in like before. Okay. Cool. Tough question that though, really tough. Okay, we'll keep moving. Right, we got ourselves 2 questions here. So particularly the dy dx is what we're interested in. So for the sake of time, I'm going to keep pushing along. So what do we got here? So probably a product rule. Okay, you could just go u and v here when we're taking derivative. But what they say first of all is just find y when x is 2. Okay, so everyone should be all right with that. You just put 2 ln to be like the number 8 because 2 to the cubed is 8. Okay, that's fine, and you can write 4 decimal places. Okay, so get dy dx right in this format. So what we'll do here is we'll use a product rule. We'll call that u and we'll call that v. So u, be neat for the examiner, u is x, v is ln x cubed, du, I need to be a bit neater here, du, dx is 1, dv, dx. Now what's the derivative? How do you take derivatives of natural logs? So the way you do it, it's very straightforward. You just go 1 over whatever is in there, doesn't matter what's in there, whatever is in there, and you multiply by the derivative of what's in there. And what's the derivative of what's in there? It's 3x squared. Okay, and then we sub that into our product rule, which is really easy to remember. It's just like u times the other guy derivative. We can cancel this down here, so this is just like a 3 over x. Hopefully people can see that, because it's an x squared on top and x cubed on the bottom, so they cancel, just leave an x on the bottom. And then it's a plus the v times the du dx, which is a 1. So I can just write a 1 there. Okay, so then this tidies up to be x over x here. So that's just cancels and they leave the 3. So then you really get 3. Sorry, let me be a bit neater. So dy dx is equal to 3 plus ln x to the 3. And we should all know one of the most important rule of logs is that this power can just pop out the front. So if this doesn't ring a bell, you should go revise your logs in your algebra book. So the 3 can just pop out the front like this. It's a really important rule of logs. And so then yeah, that's that done there. Okay. Right. Keep moving. Yeah, so this is a good one here. So really happy that they asked this here in 2023. So people would look at that and they might say, oh no, we have to go use a quotient rule here. You don't. So when the number on top is like a 1 here, or even if it was a 10, if this was a 10 on top, any constant number like that on top, the process I show you here is the same, okay? So what you can do is you can rewrite your f of x, and you write it as whatever the number is there. If it's 10, you write 10. If it's 1, you write 1. And then you bring the bottom up like this, as I've shown earlier. We call it to the minus 1. And then we can just take a derivative of this without doing any quotient rule or product rule, because this is just a constant. As I said, this constant will just be multiplying the answer at the end. So if that's a 100, if it's a 77, you'll just write 77 here. And then the main thing you're taking the derivative of is this here. So the way we take the derivative of this is we multiply down by the power, keep the inside exactly the same, reduce the power by 1, multiply them by the derivative of the inside, which is a 10x. Okay? And so then f dash x will be equal to, hopefully you can see why it's minus 10x on top, and then a 5x squared plus 7 all to be squared on the bottom. Right, where did I get that from? Well, we can see that there's a 1 times minus 1 times 10x, so there's a minus 10x on top. So we could have left the 5x squared plus 7 to the power of minus 2 on top, or should we just bring it underneath where it's neater with the positive power? And that's it in its simplest form. Great. Really important question for people to see there. G of x, this isn't related to this up here. No, it's not. So this is just another nice question. What's the video on there? Of course, it's all gone over an hour. I don't really like them going on over an hour, but yeah, I might stop this and make another, after I do this question, I might stop this and make another part to this. So yeah, let's do this here. So g of x is these two things multiplying one another. Basically, it just says work out g dash x. So hopefully people can realize you can just use a product rule here. Okay, so let's do that. So u equals tan x over 2. V equals ln x. We have then du dx. Now what's the derivative of tan? So that's sec squared, and the inside stays the same, and then we multiply by the derivative of what's in there, which is 1 over 2. And then dv dx, the derivative of this, as we said, is 1 over what's in there, multiply by the derivative of what's in there, derivative of x, just 1. So that's why the derivative of ln x is 1 over x. Okay, so then this is, we don't say equal to dy dx here, we say it's equal to g dash x because the function was called g of x. So we say g dash x is equal to u times the derivative of the other guy, which is I'll put a square bracket on this for neatness, times a 1 over x. Then it's always plus. Then it's the other guy, ln x, it's the v, and then multiply by the other guy's derivative. So what I'll do is I'll bring the half out the front there, and then I'll call this sec squared x over 2. Okay, great. So then, yeah, a bit of an annoying task now. You got to go and put the half pi over 2 in here. So I'll do this up here, g dash pi over 2. Okay, so hopefully people are okay with their algebra and realize that that's going to become pi over 4. Because it's a bit like pi over 2 multiplied by a half, pi over 4. Again, you should be probably okay with that. And then, okay, so if x is pi over 2, 1 over x is 2 over pi. So a nice bit of algebra there for people, nice trick. Okay, then it's plus 1 over 2 ln pi over 2. And then we have a sec squared, same thing again, sec squared pi over 4. Okay, so then you can just type that into your calculator. Some things you should know here. You should know tan pi over 4 is 1. So that's a 1 times 2 pi. This here doesn't really simplify much, so that I'll see what sec squared pi over 4 is. I don't know. To even type sec into a calculator. The sec button is somewhere there, but just so people know a trick here, let me clear this away for a second. So if you can't find the sec button, you can work out what sec actually is. Um, so sec is actually 1 over cos A. So sec squared A is equal to 1 over cos squared A. So if you wanted to get, I think what I'm trying to get here is sec squared pi over 4, and you can't find the sec button in your calculator, it is the exact same as whatever 1 cos squared pi over 4 is. And of course, the way you type that into your calculator is, remember that 2 is actually out here like this, so it's like squaring everything on the bottom. So let's actually do that. So we go 1 over something on the bottom being squared, and that thing is going to be cosine pi over 4. And I get the number 2. So that's working out as the number 2 for me. Okay, so yeah, looks good. Again, see can you find the sec button on your calculator and work that also out to be 2, but it's actually quite nice people seeing that alternative way of typing sec into a calculator by turning it into a cos. So then this here is 1 over 2 ln pi over 2, and then as we said times the number 2. That's great because it cancels with the half there, so then this just becomes 2 over pi plus ln pi over 2. And yeah, that's fine because a here is 2 over pi, which is a real number, and b here is pi over 2, which is a real number. So cool, that'll do me. So I'll probably stop the video here. Let me just see how many questions have a mark left beside them. So we just done that one. Yeah, there's a few more. There is a few more, so I'm going to stop here because it's gone over an hour, and then we'll pick up in the next question from in the next video from. Let me zoom in here. Just done that one, so this will be our next problem. Okay, so I'll stop the video here. Okay, so we're back for part 2 of important differentiation past paper questions you should know. So an easy enough one to start off with here, but still worth doing because this looks similar-ish to another type of question where you could have something like it could be a log e and it's actually x over something like x squared plus 1. Okay, so in this scenario here, you'd apply like a rule of logs, first of all, where you'd like rewrite this as log e x take away log e x squared plus 1, and then you take the derivative of these two guys, you know? But that's not what this is here. This is just a straight up quotient rule, okay? Or you could use the kind of the new snazzy way I'm showing you of bringing the thing on the bottom up. If that's x squared on the bottom, it'll be x to the minus 2 when it comes up. And like always using the product rule, not needing to use the quotient rule. Okay, so we'll call this u, we'll call this phi. U equals ln x. Oh, v equals x to the minus 2. du dx being neat is 1 over x. d v dx is you multiply down with the power, minus 2, and you reduce the power by 1. Great, so then we sub that in there to our product rule formula, but it's pretty easy, remember off by heart, just go u, multiply by the other guy taking a derivative of, and then it's always a plus, and then it's v multiplied by the other guy taking a derivative of, which is 1 over x. And now we can absolutely simplify this up. So how could we say I ran out of room down the bottom there, so I'm just going to write what I'd be writing down the bottom up here. So this is ln x, so this here I would write as minus 2 ln x over x cubed. So you just bring the minus 2 out in front, and then x to the minus 3, bring it down the bottom. And then this here is actually 1 over x cubed. So the reason that is because this here is 1 over x squared. 1 over x squared multiplied by 1 over x is 1 over x cubed. Okay. And yeah, you can write them because they're both x cubed in the bottom. You could say it's 1 minus 2 ln x on top all over x cubed. If you want to write it as a single fraction. F dash 1, that's just putting 1 into it. I don't think you need to see me do that. It's junior cert stuff. Okay, so this seems to be another function. Yeah, this is another thing. So they've kind of come up with something else here, okay? This must be a mock exam because if this was a state exam, they wouldn't also call it f. They'd call it maybe g of x, you know. But sure, we'll go with what they give us. So they say this other function f dash x is equal to 1 minus 3. That is not x dash, that's a comma. So again, that's really badly typed up. Stupid mocks. So yeah, it probably wants us to integrate here and find f of x. So they've given us an initial condition here, so that will help us find the plus c. So first of all, we can just call that dy dx. It's a neater notation. Dy dx is 1 minus 3 over x. And so then what we're really being asked here is to integrate this. So then the integral of that there becomes f of x. And we're integrating 1 minus 3 over x. And don't be the students that are forgetting to write dx, you know, because it's technically not correct if you don't write the dx there. Right, f of x then becomes, we can integrate this, the integral of 1 becomes an x. Now this is a tricky one here. So the integral of 1 over x. So that's not, you got to watch out for that one. Okay, the integral of 1 over x is, now we've 3 over x. Whatever the integral of 1 over x is, it'll be the same as 3 over x, just multiplied by 3. So be on the lookout for when you're integrating 1 over x, guys, because it turns into ln x, okay? And it's got the modulus thing there, so do actually include that as well, to be perfectly correct. So yeah, so just be on the lookout for that. So this here is actually, as I said, the 3 is just going to, it's a number, it's just going to be multiplying whatever the integral of 1 over x is, and then that is ln, and as they say, it's good to put the modulus in there. And then it's a plus c. So then we have that f of e equals minus 2, and that will equal when we, so yeah, it's actually the neater to write it like this. So then to write minus 2 equals, putting e in here for x, e minus 3 ln modulus e. Now the modulus of e is just e, so we can just tidy that up here in the step. And we should all know what log e is. It's 1, just like log 7 is 1, you know. With the base and this thing here are the same, and you just get the number 1. So then that really tells us, and not forgetting our plus c then. So then this tells us minus 2 equals e minus 3 plus c. So then I'm seeing c then is something like 1 minus e when you bring the 3 over. 1 minus e. Yeah, that'll do me. So then I'll call f of x then equal to x minus 3 ln x in the modulus, and then our c, which we just worked out, which is something like 1 minus e. And then circle that up for the examiner. Okay, that'll do me. So that was a good question. That's, you know, it looked so simple that, but it actually had a few steps to it there. So that'd be a great pass. That'd be a great question to come up. This was in a deferred exam, and this is a nice little function here. They ask a few cool questions on this. So I will do this because it's, I think our differentiation part only comes up here towards the end, but it's just a general good question for students to see being solved, okay? If you've never done this one. So there's some function here. Obviously pause the video and do the parts as we go along, you know. And what I'll do is, like what I done previously in the part 1, is where we kind of take a snip of the question and we keep it coming. So the part 1 here is find the number of trout in the lake when it was first stocked. So it's, if you've done enough past paper questions, you see this kind of thing repeating all the time. That's just basically put in 0. When it's first stocked is when time is 0, you know. So then that's just equal to 3000 over 1 plus 6.5 e to the 0. Okay, because that, and anything to the power of 0, anything to the power of 0 is 1. So this is really 3000 over 7.5. And then that works out as, should be a whole number. 400. Okay, there's 400 trout. It has units as well, so you do need to say trout. Okay, sound. And then part two is probably, oh, how many are there after? Yes, that's all. These questions are always the same. It's just get you to like find the approximate number of trout at the end of the 10th month. So it's just like n of 10. So I don't think you need to see me put 10 in there. You can all do that. Show that the number of trout has a limiting value of 3,000. So I want everyone to pause the video and have a go at that and see how you would show that. Okay, a very, very important question. Right. So, it has a limiting value of 3,000. So how did you go about doing that? So the idea is here, this is the only thing that has a t in it, right? So this is the only thing that can kind of change value. The rest of it stays the same. So you're really just focusing on what's the limiting. The question is, what does e to the minus 0.814t take on as values? Okay, so that part there is an exponentially decaying function. Okay, so we're going to study its values. So as we explained, when t is 0, this thing gives a value of 1, right? But as t goes on, like as time goes on for infinity, you should know that if you put t in as infinity here, this thing will go to 0. So what going to infinity means is what value will it have as you move all the way out on the x-axis forever and ever and ever. And this thing's an asymptote to the x-axis out here, so it'll take on a value of 0 when the y value will be 0 when the x value goes off to infinity. Okay, so this thing here, you just kind of explained for the examiner, is that e to the minus 8.14 when it goes off to infinity will give a value of 0. Okay, just kind of explaining as well why that does that. So when you have you're getting all sorts of indices stuff practice in here. This as a number with the t is the same as 1 over e with a positive power, right? And you put infinity in for t like we're doing here. What this becomes is 1 over e to the infinity. Now, if you put anything to the power of plus infinity, the thing becomes 1 over infinity, and 1 over infinity, as we covered in the previous video, is 0. So that's why this thing gives a value of 0. So you just need to show, like this, if this was my workings, I'd get full marks for this, because I'm basically showing that as t gets big, as t goes to being big, this thing goes to being 0. And so then what it's really working, you could say n infinity goes to 3,000 over 1 plus 6.5 times 0. And so that equals 3,000. And that's the limiting value. Great, that's fair. You can pause that and you can rewind that and it makes sense of it, but that was a good explanation for you there. Month n is the first month when the number of trout has risen above this. Find n. So will I do that? So this is a question where they give you n and they make you work back to t using some snazzy algebra. So 1 plus 6, so as you can see here, I have written one equation with how many unknowns? 1t. So you should be able to move this around and get t. So I'll just show you the algebra steps on it. Bring the bottom up there, bring this guy down under the 3,000. So you get 1 plus 6.5 e to the minus 14t. And that will be equal to 3,000 over 2,650. What you'd do then is you'd bring the 1 over and divide by 6.5. So I'm doing a lot of aggressive steps here in one go, because I want to just move on from this. This is just basic algebra you should be able to do. Take the 1 away, divide the entire thing then by 6.5. That's a number. You could type that number in your calculator to get an answer, or you can be like what I'm doing here and just be really aggressive with it. And you can just put it into log format. So 0.8, I better get a number so that people can follow along. So let me type that into a calculator there. 3,000 over 2,650, take away 1, divided by 6.5. So what that becomes, it's e to the minus 0.814t. Do not write this as a decimal, write it as 14 over 689. Put it into log format. The whole thing of logs is to get the power on its own. The power is this, so this will be on its own. What's the base here? The base is e, so the base is still the base in the log. And I already showed this in part one of the video how to quickly write things in log format. And so this then is equal to t, and then in your next line you'd then divide whatever that is there. That's ln 14 over 684 divided by minus 0.814. I'll get you an answer for that. So ln 14 over 689 over minus 0.814. So I'm getting, it is 4.79 months. Now you're asked what is the first month, so you got to be careful with this. Has risen above, okay? So there's two options when you do this with the logs. It's either month 4 or it's month 5. It's not just a matter of round up. You've got to be very careful with this. Now the answer actually is 5 in this question, because if you put 5 into the original function, you'll see that the number goes above this. It'll be something like, 2700 or whatever. If you put 4 in for t there, you'll notice it hasn't gone above 265. So this isn't the answer. But if the question was worded a different way, right? This is when it would actually have been the 4 as the final answer. So you're always meant to check this. The question will be, find the last month when the number of trout is still below 2650. And the last month is month 4. Okay, so you would do the exact same calculation we've done, but then you'd evaluate both your answers and you'd see that when you put 4 in there, that is still below 2650, and this goes above 2650. So this would have been our answer then if the question was, find the last month when the number of trout is still below 2650. So again, none of that is differentiation, but it's all stuff you should know. Find in terms of t the rate of change, the rate at which the number of trout is increasing at. So this is what we want. So we want to take a derivative of this. Now, a lot of people would be super scared and they would just go and use a quotient rule for this. And that's kind of, yeah, if you want to do that. But because the thing on top is a number, there's no need for a quotient rule here. Okay, but you can do a quotient rule if you want. What you would do here is you just rewrite your n of t. You would bring the bottom up like this. 1 plus 6.5 e to the minus 0.814 t to the power of minus 1. You can just bring it up like that. And because this is a number 3, this does nothing. This number will just multiply whatever the answer is, the derivative. So we're really just, n dash t is really whatever the derivative of this is in here, and multiply by 3000 at the end. So as I said, the 3000 does nothing. It'll just multiply whatever the derivative of this is. So how do we take a derivative of this? We multiply down by the power, keep the inside exactly the same. This is the chain rule. Inside the exactly the same. 1, 4, t. Now it's reduce the power by 1 to 2, and then we multiply by the derivative of the inside. The derivative of the inside here, the derivative of 1 is 0. It's nothing to write there. Derivative of this will be 6.5 e to the minus 0.814 t. It stays the exact same when you're taking the derivative of an exponential, and then you multiply by the derivative of the power, which will be minus 0.814. So that was quite intense. Taking a derivative of that. So yeah, and then you put a square bracket there. So yeah, there was a lot to that. So yeah, and then in terms of t, so I'm not going tidying that up because it is in terms of t. But you could tidy it up if you wanted. So yeah, so that was quite intense. So what you could have is, if you did want to tidy it up, you could have your n of t. You'd have your minus, you multiply in the 3000, you get a minus the things to the power of minus 2, so it's really just the same thing squared on the bottom. 1 plus 6.5 e 814 t. And then it's multiplied by these things. So yeah, it's multiplied by these things, so then it's like 6.5 e to the minus 0.814 t on top, and then there's also multiplied by 0.814. And then if you wanted, you could work out, oh yeah, then it turned into a plus, so you write it as a plus, and then you do 3000 by 6.5 by that number in your calculator. That's pretty tidy. Okay, cool. Right, this is like what I spoke about there before we done that log question at the very beginning of the video. So everyone should pause this and give this a go. Right. So what you don't do, so if the, what we don't want to do here is like if say I'll give another example here so I can teach people this. Say we had ln 3x squared plus 1, right? We probably would just go straight in. We would go straight in and just take a derivative of this. The rule for taking derivatives of natural logs is you go 1 over what's in there multiplied by the derivative of what's in there. And the derivative of what's in there is a 6x. And you're done. So the answer to that is this. Okay. So if you go and you try and do that same thing up here, things get pretty intense pretty quick. So technically the derivative of this would be 1 over what's inside of the log. So that's already pretty intense. So you have 1 over a square root of this thing. But the huge problem now comes is you have to multiply by the derivative of what's in there. And that's tricky because it's a quotient rule out. It's like it's a quotient rule inside, and then it's also all to the power of a half. So there's a lot going on there. So surely there's an easier way. There is. So you just use your rule of logs. So what this is, you just rewrite y. So everyone, if you don't know your rules of logs, you should. That's a hint now to go and look at the textbook and revise your logs. Something that's to the square root is the same as being to the power of a half. There's a rule that for logs is when the power is here, it can just pop out the front. So that's a half ln 5x over x minus 2. And then there's another rule for logs where if they're dividing in here, they can be split into subtracting. So you put a square bracket on the half, and then you have an ln 5x. There's no need for a square bracket here. ln 5x take away an ln x minus 2. Okay. So then you can take a derivative of this, and it's going to be so simple. So then dy dx, the half does nothing. The half will just be chilling out there. It does nothing. So the derivative of this is 1 over what's in there, multiplied by the derivative of what's in there, which is 5. Take away 1 over what's in here, multiplied by the derivative of what's in there, which is 1. And then, yeah, we can then multiply in by the half, and we'll see that dy dx equals the 5's cancel, so you get a 1 over 2x. And then this is take away 1 on top here, 2 times x minus 2. And then if you wanted, you could write it as a single fraction, but they didn't tell us, so that's me. Okay. Good question there, really good. Make a flashcard on that, revise your logs if that doesn't make sense. Where did I get those rules from? If you go to your tables book, you'll see the rule I applied for separating them into a minus. You see this really important rule here where the q can just pop out the front. That's what I done at the beginning where the half came out the front. Great. So yeah, find the derivative of this. We will do this. It's super simple. It came up in 2022. So you'd be rubbing your hands together if you got something as simple as this for 5 marks. So what you do here first of all is you rewrite g of x. So that's an x to the minus 1 there. Okay, and then you take the derivative. So g dash x equals 2x minus, so you multiply it down by the power, so that'll give it a plus now, and then it's x to the minus 2. Okay, so hopefully people are okay with that, and then you'd rewrite that as 2x plus 1 over x squared. Whoop, whoop. Okay. Yeah, that's fine. Yep, keep moving. So find the derivative of this. So yeah, this is really good because there's actually 3 parts to this. So there's this here then as well. So let me try and somehow get all 3 of them in our line of sight. There we go. Right, so we've been given these 3 questions to do. Pause the video, have a go at all 3. So the first one's a bit of a gimme. It's straightforward stuff. dy dx is 3 plus cosine x. Okay. Derivative of that is just leaves the 3, and then the derivative of this leaves goes cosine x. Okay. Now this is an inverse cos, right? So you got to be careful with the inverse causes. So they're not too bad when they're written like this, because this is like x over a. So you can just actually follow that from the tables book here. Inverse x over a, you just follow that there. Okay, so let me somehow take a snip of this because I'll need this for the question. Okay, and then we're going to go back here maybe. Yep. Scroll up there. Oh no, I know what I've done here. I had that like that maybe, and then Both of these were open. Ah, yeah, that'll do. Okay, so this is easy enough. You can just follow the rule in the tables book for this and kind of sub it in. So the differential of this, again, we'll call it y. All of this is equal to y. So then dy dx is literally just follow this here because a is 4. So then this is equal to minus 1 over the square root of 16 take away x squared. Putting 4 in for a, and you get your full marks there. Now the problem is this here is not in that format, okay? So you can't use that kind of quick rule that we done up there. So when you're taking a derivative of something like this, okay, it's kind of the same as if you were taking the derivative of something like x squared plus 2 here, right? It just does not follow the rule here, okay? This is not as simple as like x over 4. Both of these are much more complicated. So what you got to do here is the chain rule, but we do the chain rule in the kind of the long way, right? So what you do is, I'll actually solve the red one here, just so people can learn from this. So this is equal to y, right? That's our y. We make a substitution called u. We say u is equal to x squared plus 2. So this is actually how the chain rule works, if people aren't aware. We then we sub in our u, because we've defined u as x squared plus 2, so then we can say this is cos inverse u. And people should be okay that if that's a u there, it's really like u over 1, which will be important for this over here in a sec. Okay, so I'll write it like that first, and then just remind people that a u is u over 1, you know? Now, what we really want is to be able to take a derivative of this thing in pink, right? And so we want to get dy dx. And the way we get dy dx is from this really important thing of we can actually pull this apart. We can pull this apart by putting the dy there and the dx here. If you've never seen this now, I recommend going to the book and revising this chain rule thing. You can pull your derivative apart like this. And then you have the option to put whatever you want here. You can put a 7 here, and the 7 would cancel down, and it goes back to dy dx, as you'd imagine, okay? So you can put whatever you want in there. And because we've called something u, it makes sense to call this du and this du. So then the thing we're looking for in pink, dy dx, is really just a matter of getting these two things and timesing them together. So dy dx will come from timesing these two things together. Where do we get dy du? We get dy du by taking the derivative of the function that's y in terms of u. So then dy du would be basically whatever the cos inverse of u over 1 is. And this is in this format here of x over u over a, basically. So in for x we put u, and in for a we put 1. So you get minus 1 over the square root of 1 minus u squared. That's him. Okay, so now we also need, I'll get a different color, we also need du dx. So what will du dx be? We will get du dx by looking at a function that's u in terms of x. So then du dx here is 2x. And then we just sub these things in. So let me get another color. So then dy dx is dy du, which is this thing here. So people should have seen at least an example. If you don't, you would have been taught this in the textbook at some point, you know. So good to revise this. So I'm just subbing in dy du, and then I'm subbing in du dx. You don't leave your answer like that. You replace whatever u was at the beginning. So u is this thing up here. So your final answer will be minus 2x on top over the square root of 1 minus, in a bracket, x squared plus 2 squared. Okay, so that's how you do that. And you can multiply that out if you want, but I'd leave it like that. So doing the actual question we were asked up here, we do the same thing. We say u equals 4 over x. So remembering y was equal to cos inverse 4 over x. So then y becomes cos inverse u like before, right? So then what are we really looking for? We're looking for a derivative of this pink thing. So then we want dy dx. The thing we want is the thing we pull apart. And we pull it apart by putting that there and that there. And we can put whatever we want here, but it makes sense to put a du here. And so then we get our answer by just multiplying these two things again by one another. Now, this is an interesting one here. See how u is. So I'll get the du dx first of all. So let me try and get the colors going. U is equal to 4 over x, as we said. But we can rewrite that as 4x to the minus 1. to take its derivative, and then we can get du dx, which will be minus 4x to the minus 2. Hopefully people are okay with that. And you could even tidy that up. You could call that minus 4 on top and an x squared on the bottom. Basic enough differentiation. People should be able to do that. Okay, so then what we also need is dy du, which will come from taking the derivative of this blue thing here. I'll use red. Dy du, because that again is in the format u over 1. We can just follow this here, and it'll be putting u in for x and 1 in for a. It'll be 1 over square root of 1 minus u squared. And so then subbing into the pink thing above there, I'll use black. Dy dx, the thing we're looking for, is equal to dy du, which is this thing, minus 1 over root 1 minus u squared, times du dx, which is this thing, minus 4 over x squared. We don't leave our answer like that. We swap u out with what it originally was up here. And so our final answer for dy dx will be minus, we can multiply out the top. It's easy done. It'll just be a plus 4 on top. And then it's an x squared here multiplying a square root of 1 minus 4 over x squared. Cool. And you could tidy that up if you want to call it 1 minus 16 over x squared, but it's just as tidy that way, you know. Yeah, you could actually, yeah, if they were on your case there to tidy that up, I could show you one more algebra step to tidy it up. You don't need to do this here now, but that can be written as 4 x squared square root. No, that'll do. Yeah, the black thing is the answer. Okay, cool. So again, if you've never seen how to take the derivative, they don't come up that much. You'll just really see them in mocks, but they're absolutely due to come up on a state exam. And that thing there, where I'm using the chain rule by subbing in u, you're meant to know that. There's other applications questions, the differentiation, particularly they're called the rates of change question, where you've got to be able to do that pulling apart thing I done. Great, so we'll keep moving. How am I doing? 29 minutes, good stuff. So what do we got here? We're told that these two things are multiplying, and then we're told to write dy dx. So, looks like a product rule, doesn't it? Unless you know a trick. So, let me show you a trick. You should know this off by heart, that sine 2x is 2 sine x cosine x. And you should also know the other one off by heart. Cos 2x is equal to cos squared x minus sine x. Now, what's important about this one is you should know that a sine x times a cos x is actually a half. You just divide both sides by 2. A half sine x gives you sine x cos x. So then I could just rewrite y here. I could just say that y is actually equal to a half sine 2x. And so the half doesn't do anything when I'm taking a derivative. It's just a number. It'll be there at the end. So dy dx will be just equal to a half times whatever the derivative of this is. What's the derivative of sine 2x? It becomes cos 2x, keeping the inside the same. And then we multiply by the derivative of the inside, which is a 2. And so the answer is cos 2x. Done. Okay, if you didn't know that quick rule, obviously you have to go and do a u and a v here, product rule. So u equals cosine x, v equals sine x, du dx is minus sine x, dv dx is cosine x. Sub them in, d to the product rule, dy dx equals u times the other guy, so that'll be a cos squared x. And then it's v times the other guy, so that'll be a minus sine squared x. Oh, remember, what did I have there a second ago? You should know that that's cos 2x. Cool. Where do they come from? They come from your tables book. There they are. Look at them. I'm circling them with my mouse. You shouldn't need to go to your tables book to look at them. They should be just in your head. Okay. If you want to be a good student. Okay. Yeah. So this is these are a bit miserable, but they come up quite a bit. If you've been watching me scroll through the document, these first principles questions come up, and they're really easy marks. But there's places you can get marks deducted for not being neat or technically correct. So I have to do at least one of these, even though they're pretty boring. Okay. So I suppose I'll have to do one just to show you how they go down. Okay, so you have to be neat. Okay, as I said, these are straightforward and you got to do them properly. So you're asked to differentiate this from first principles. So the very first thing you'll do is you'll say f of x equals 17 minus 4x minus 3x, okay? If they don't already say that that's f of x in the question. You then are really looking for f dash x, right? And you got to know this formula off by heart, that it's the limit as h tends to 0 of this formula, f of x plus h, take away f of x all over h. Now, to be able to sub into that formula, you need to go, so this is literally your step by step, that's step 1, step 2 here. So you got to go and work out your f of x plus h. So you do that by going 17, 4 minus x plus h, replacing x, of course, with x plus h, minus 3 times x plus h squared. Again, you want to be really neat here. You want to make sure you're always stating who everyone's equal to. So this is 17. I'm sure everyone can multiply out. I'll do it quickly. This here is minus 3x squared. I'm going to do this quickly as well. When you square this, you square the first term. Then you multiply them together and double it. So that will be a minus 6xh when you bring the minus 3 into the equation. And then it's a h squared. So that's a minus 3h squared. Right? What you do then is you sub f of x and f of x plus h into this formula. You be very clear about what you're doing. This is now on the left f dash x, and this is equal to, you got to state this, limit as h tends to 0. It's not correct if you don't state that, over f of x plus h, so you do got to sub all of that in there. It's pretty annoying. So it's 17 minus 4x minus 4h minus 3x squared minus 6h minus 3h squared. Okay, all over. So this is then minus f of x. The quick way to do this is just change the sign on everyone there. So you just write minus 17 plus 4x and then a plus 3x squared. And then it's all over h. Now you know you've done this right if everything that doesn't have a h in it cancels. The 17's cancel, the 4x's cancel, the 3x squareds cancel. So everything that has a h that doesn't have a h cancelled. Now this is where people lose marks. So they don't write limit as h tends to 0 again. And you do have to write it because you haven't actually subbed it in yet. So you do have to say it. Limit as h tends to 0 again. And then on top here, what do we have? We have a minus 4h left. We have a minus 6xh and a minus 3h squared all over h. Right, we're going to do a bit of cancelling, obviously. But still, look at this. We still have to say limit as h tends to 0 because we haven't actually put it in yet. Okay. Now we're cancelling down, so there's no fraction anymore. We're dividing in the h. So it's really a minus 4 there. It's a minus 6x, and then it's a minus 3h. Now look at what we're going to do. Now we are going to put h in for 0. So we're going to put 0 in. And once we do that, we then stop saying the limit because we've actually put it in. So we show the examiner minus 4, minus 6x, and you show yourself putting 0 in for h like that. And you get your full marks then by writing FC, you've got to keep something going on the left here every time. F dash x equals minus 4 minus 6x. And of course you can check if you've done that right. You just take the derivative of this up here. If that's y, dy dx equals, that goes to 0. This is minus 4 and then this is minus 6x. Boom, it's definitely correct. Okay, they're the steps, and you have them all going vertically down like that. Line, 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 line. Okay. Great. They come up, so nearly every second year, so you got to be on top of it. Right, why have I picked this here? Probably because I want to show you completing the square. If anyone doesn't know how to complete the square, you'll learn it from this here. And then there's also, so this is actually mainly an algebra question, but it's tied in. This is 2021. It's a smart question here. They're revising a lot of things here in one go. So they're testing out, can they take a derivative of a basic thing? Then they're seeing, can they complete the square? And then they're seeing this other important thing about an inequality in part 2. A lot going on. Right, so let's do this. So the derivative of this can be expressed as this. Okay, so do that. So pause the video, give a go at both things here. Okay, so hopefully you had a go at that. So f dash x obviously is 6x squared plus 12x minus 12. Now we've got to complete the square on this. So if you don't know how to complete the square, you've got to go back to your algebra book and learn it because it's a really important thing to know how to do. So in a scenario like this here where x squared doesn't have a 1 in front of it, you factor out whatever's in front of it. So this is a nice question here because these actually are a factor of 6 as well, like such. And then what you do is you complete the square on the thing on the inside, keeping what it is on the left going here. So it's 6. So what we do is we half what's in front of the x. So we go x plus 1 squared like this. When we square this out, the number at the end will be 1 squared. We kill off that, so now we have no number, and we put the number we want in here, which is a minus 2. That's the best way to complete the square. So then this is equal to 6 bracket x plus 1, and then you combine these two things. If they're complicated fractions, you use your calculator, but they're obviously just minus 3 now. And then what you do is you multiply in by the 6 then that you took out at the very beginning. So then it's 6 bracket x plus 1 squared minus 18. And then we know a, b, and c here. So a is like 6, b is 1, c is minus 18. Now, you know you've done this absolutely correct. You want to definitely check this in an exam. Multiply all of that out there that I've just circled in green. And if it does not become the original thing up here in red, you know you haven't completed the square correctly. If it does, you know you have, and then you're happy. Okay. So now the next thing here is we're told, this is another kind of algebra question now. F dash x is greater than g of x. Find the range of values for which this happens, right? First of all, we'll get whatever g dash x is there. Hopefully everyone can see g dash x is just 36. So what they're really asking, and it's more useful not to have this in the completed square format, is it? Or could that be useful? I'll go with it not in the completed square format because this is just a general question then. So what they're saying is, following their instructions here, f dash x is this red thing. 6x squared plus 12x minus 12. That thing we're looking for when it is greater than g dash x, which is 36. Right. You can divide everything by 6. You're allowed to do that because it's a plus number. If you divide both sides by a positive number, you don't need to change this. If you divided it by minus 6, you would have to change that. It's direction. Plus 2x minus 2 is greater than 6. Bring everyone to one side. Minus 8. What you do then is you factorize this. Okay, so then this is x, this is x. This is probably going to be a plus 4 and a minus 2. Minus 2. Now, this is really important. Your answers are not, you can write them in a corner up here of the page. So you can say x is minus 4 from that and x is 2, but they are not your answers. The way you interpret these is you draw a number line, like such, and you draw 2 dots on the number line. The most left point, it'll be whichever x value occurs first. Minus 4 is further left on a number line, and then 2 is further right. What you do then is, was this a u or an n, this quadratic? This is a u-shaped quadratic. You should all know that's a u-shaped quadratic because it's a positive, the coefficient of the x squared is positive, so it's a smiley face. Now, this says this thing is to be what to 0? Greater than 0. When it says greater than 0, what you do is you shade in the parts of this curve that go above the number line you drew, and then you just describe the orange regions. So the orange region to the right is described by x greater than 2. This region to the left here is described as x less than minus 4. And they're your two solutions, which they're really one solution, you know, that's the range of values. Okay, if that doesn't make sense, you've got to go back and revise them in your algebra book. They're a pretty big thing, these, okay? They come up maybe every second year, every third year, okay? They're the quadratic inequalities, they're called, and you got to know how to do them. Okay, so again, that's what this video is all about. It's a past paper questions you should know. Right, so we got a one here in 2021. What do we got? So we've got a exponential function. That's exponential decay. We should be able to graph this, people. Pause the video and have a go at graphing that. Okay, so where does it cross the y-axis? It'll cross the y-axis here. Remember, this will be small t here, and then this will be big T for temperature. That's time. What do we got? So when we cross the y-axis here, it'll be when the small t is 0. You put a small t is 0 in there, then it's e to the 0. which is 1. And so this will be 75 plus 20. And so then this will cross this axis here at 95. This is exponential decay. So you should know it decays down like this. Now, does it decay down like this where it gets really close to the x-axis? The answer is no. So this part of the function will decay off to 0, okay? That will decay off to 0, as we talked about this earlier in the video. When x goes to infinity, that will go to 0. So then it'll be 75 times 0 all the way out to the right. But there's a plus 20 here. And so that just ups its value from 20. So it doesn't get to touch the x-axis there. So the graph of this would look something like this. It decays off, flat line eventually, and it flatlines to this asymptote here at a value of 20. So that's the graph of that function there. Yeah, you should know that. Okay, that's if that's super confusing, you got to kind of revise your exponential graphs, and you type that into. You should be typing stuff into Desmos as well and seeing what things look like. Anyways, find the nearest degree Celsius the temperature the copy has reached when this. Okay, when this is equal to this, where this is the rate. Okay, so again, we'll just kind of follow an instruction here. This is a really interesting question because they're not actually looking for the rate. They told us the rate. They're looking for the temperature of the coffee. Right, so they're actually looking for the original T. So they gave us this instruction so we can go off and get the time when this happens. So give this a go, of course. Pause the video. So we'll work out this because we obviously need it. So the 75 does nothing. It'll just be there at the end. The way we differential take derivatives of exponentials here is they stay the exact same. And then we multiply by the derivative of what's in the power. And the derivative of that is minus 0.081. Derivative of 20 is 0, which is constant. So that's that. And then we're told to set this thing equal to 0.81 times minus 0.081. We're told to set that equal to this number here, because that is this here in pink on the left is t dash t. So you can see a t has disappeared. There's the t. So this pink thing is one equation, one unknown. So we're really looking for t here. So a bit of algebra to get the t on its own. So what we'll first write is 75e minus 0.81t is equal to this number over 0.081. Obviously they're both negative, so we'll just call it a positive. And then we got to bring the 75 underneath here. So I'll actually do that as well on the same line. We divide both sides by 75, so the 75 will be chilling down here. So obviously you could type that into a calculator if you feel more comfortable working with it as a number. So I'm going to be aggressive with this one and not do that. So the power will go on its own. That's the whole point of logs. We need logs here because the thing we're looking for is in the power. Okay. And that will be equal to log. The base stays the base. The base here was e, so the base here will be e. And then this here will be this number, 405 over 75 times 0.081. And then t then, so the examiner would like this if you don't know this. So this log e is ln, of course, 4.05, because you're not working with rounded decimals as you go along. This is like an exact answer, and then you divide everything by minus 0.081. So great if you can move the numbers around like that. That's the ideal place you should be, Yeah, 75 multiplied by 0.081 over minus 0.081. So t works out here pretty nice to 5.0057, and t is in is it in hours or minutes? Does it tell us? This is surely it told us this, yeah, per minute, so we know it's in minutes because this is a state exam. Now that's not actually what we want, okay? That's just the time when this rate happens. So what we're actually looking for is, to the nearest degree Celsius, the temperature of coffee when it's reached this. So we've got to actually know that what we're looking for is a big T here. And the way we get that big T is by putting this in. Okay, so we put that time into the original function. So we go T of 5.0057 equals 75 this was, you know, a little bit of a tough thing for students. They'd be so happy after getting the time there that they might have forgotten to read the question again and see if that was actually what they were looking for, you know, plus 20. So the temperature of the coffee when this happens is 75 E to the minus 0.081 multiplied by our new number, 5.0057, add 20. The coffee is pretty bang on 70 degrees Celsius. So that's pretty good because that's kind of a hint that we might have done this question right when you get something so exact like that, 70 degrees Celsius. It literally is like 70.00017 for me. So I'm pretty happy I got that right there based on that. Okay, so moving along here. Yeah, this was a good question here. If anyone's not done it, look at your 2021 paper. That's kind of trigonometry stuff. If you're struggling with the trigonometry, there's trigonometry tutorial videos on the YouTube channel, so give them a go. It'll teach you how to do all them. So what I'm really interested in is just the rate of change question here. Sound. And anyone who does physics, you should be pretty comfortable with what this is here. This is yeah, you should know. This is related to 110, you know, root 2, something to do with the root mean squared power. Okay, that's for the physics people, but they should be familiar with this. Anyways, so this happens all the time where they just give you like a maths formula and you don't really need to know what it actually represents, but they'll walk you through what to do to it, you know. Yeah, so let's do this here. I will work out the period of this though, just so people are able to do this kind of thing. So as we said before, there's a really important formula where it's like it's this number here. So this is like C and it's equal to 2 pi over the period. So if we're actually looking for the period, which we are here, the period will be equal to 2 pi over C. And this is all gone. We go through this in detail in the trigonometry videos on the YouTube channel. So C then is this 120 pi. So we sub this in here. This is 2 pi over 120 pi. And the period here works out as 1 over 60 and it'll be in seconds. And so anyone who knows in Europe, our electricity is 60 hertz. Okay. So that's related with 60 hertz means 60 cycles per second. So that's why this thing does a period in 1 over 60. But you don't need to know that for the question. What you got to be able to do though is still work out the period there as 1 over 60 seconds. Great. Anyways, on to our question here in 5. Find the rate of change of voltage. Voltage is the big fee here. When t is 2. Give your answer to the nearest unit. Okay. So we just get dv dt here. dv dt. Right, that's just a number. It's not going to do anything. It's just chilling out the front. It'll be there chilling at the end of the derivative as well. So then our real thing we got to take derivative of is sine. The derivative of sine is cos. The inside stays exactly the same. And then we multiply by the derivative of the inside, which is 120 pi. Okay, and we're told to get this thing's value when t is 2 seconds and t is in seconds. So that's great. So this is basically be like 240 pi here and then multiply by 120 pi. So just be careful typing that into your calculator. I will work it out myself. 110 root 2 multiplied by cosine. Make sure your calculator is in radian mode, obviously. And multiply by 120 pi. Okay. Have I done that right? Oh yeah, no. It seems to have a bit of a mad number here, but it probably is. So it's is that right? I got a big number here. 646.05, and I'm gonna just check if it's right. Put a 2 in there. Have I typed it into my calculator right? Yeah, I'm pretty happy with that. I'm just go pause, make sure, because that seems like a big number, you know. You should always, when you get a number like this, and it's much bigger than like this here, which was just 110 times 1.4-ish, you know. So you should think about things. So let me think about this, and we'll talk about the units in a sec. So yeah, no, I can't see anything wrong there. So that number is actually that big. Okay, so let's study what its units are. So this is dv dt. What are the units of dv? It tells us that's in volts. What's the units of t? T is in seconds. So this thing has units of volts per second. Okay, so and that was a positive number, so it's like, you know, there's a huge jump in voltage per second at this exact moment here, so it's a sensitive enough moment. So yeah, that's just what it is. Okay, cool. Now this is a pretty big thing here now. Okay, so I actually put together a diagram. So people pause the video and obviously give a go at this. Okay, so you should know how to solve this. So I actually put a diagram together for when I was coming to this question. So I want people to make a flashcard on this diagram I'm going to bring up in a second, if you don't already know it. Okay, so here's this diagram I want people to be aware of. So where's my zoom controls gone? One second now. There we go. So this on top is a cubic. When you take the derivative of a cubic to get f dash x, it becomes a quadratic, and the derivative of it again, which is the second derivative, becomes a linear. Now you got to know that they actually line up like this. So we should all know that that's the point of inflection on the cubic, and these are known as the turning points. Now the turning points happen. How do we find turning points? We get turning points by going f dash x equal to 0. You should know that. And we get the point of inflection by going f dash dash x equal to 0. That's the process of getting them, right? So when we compare their graphs, look at what happens. The graph of the cubic's derivative f dash x, the roots of it will perfectly line up with where the turning points were. And the turning point of the quadratic will line up with the point of inflection. And most importantly then, for the linear, where the linear's root, where it crosses the x-axis, perfectly lines up with the point of inflection. And the reason that guy's root is because that's when the second derivative was 0. And then the reason these are 0 here, why they cross the x-axis, is because that's where f dash x would be 0. Okay. So again, if you've never seen that diagram, study it and just be aware of it and make a flashcard on it, okay? So that dash line thing is really, really important. Another really important rule of thumb is this business of being up on the right, okay? Any function, let me write any general, I'll write an x to the 4 here for the sake of it, right? X to the 4 plus b, this is a really important thing if you didn't already know this, plus dx plus e. That's any general x to the 4. This a here controls something very important to do with the function. If a is greater than 0, in other words positive, the function is up on the right. Up on the right. Right, so where did you see this before? You should know that this thing here, if we write it as y equals mx plus c, does this line have a positive or a negative slope? We know this thing to have a positive slope because it's sloping upwards. So that means m is positive, isn't it? So that means m is greater than 0 here. And yeah, that's the thing again here. If the highest power of x has a coefficient is the number in front of a thing. So the coefficient of x to the 4 here is a. The coefficient of x to the 3 is b. So it's just a number out in front. If the number out in front of the highest power of x is positive, the function will be up on the right. Where else have you seen this? You've seen this when you have something like x squared plus 3x plus 2 versus, say, this function of a plus 2 there. There's no need to write a plus, actually. Just write 2. 2x squared plus 3x plus 5. We know from our junior cert idea that this function here is a sad face and that this function here is a happy face because the coefficient of the x squared is positive. But the real thing behind it is because x squared is the highest power of x here. Because it's positive, it means the function has to be up on the right. That's why it gives a smiley face. If it's negative, it has to be down on the right. Okay? And that's the same here. If this slope was like -2, this would have to be down on the right. And it goes the same for our cubics. If the coefficient in front of the cubic is positive, it has to be up on the right. Okay? So really important stuff there. And if you don't know that, make a flashcard on it and go to the textbook on functions and remind yourself of it. So you've seen a pretty important diagram there. Pause the video and give a go at this now, knowing that new information if you weren't able to get this out before. So the idea is here, that's the turning point, and so is this the turning point. So they are the points where f dash x would equal 0. They'd be the x values. F dash x would equal 0. So this guy's derivative will have roots here. And so he has to be that guy. Okay, he has to be that guy. It's definitely not this C1 because this C1 has no roots at all. And it's definitely not this one. So the reason it's not this one is obviously because the roots don't seem to line up properly. You see how this one's really close to the y-axis, whereas this one's far away. So that's one reason. But the main thing is this guy was up on the right here, which means his number in front of the x cubed was positive. And so when you take a derivative of it, it still will stay positive. So there's no way it could have switched to being down on the right. So hopefully that makes sense to people. So you have to justify your choice. This will be the thing on the diagram here. And so you would have mentioned that they're the same locations where f dash x equals 0. So basically where the turning points occur, they are where the quadratic would cross the x-axis, have a value of 0. Okay. And you would also mention it's definitely not a because the roots don't line up as well. And then also it's down on the right. How could it be? It should be up on the right. Okay, hopefully people are okay with that. And then again, if that's confusing, you kind of need to maybe go to the book and revise some of that, you know. Okay, easy enough one here. Pause the video, give it a go. So we'll use a product rule for this. So u is x squared, v is cosine, I'm going to call it 4x to the minus 1, dv, or not dv, du dx is 2x, dv dx. Now what's the derivative of the cosine? It becomes minus sine, keeping the inside exactly the same. And then we multiply by the derivative of the inside. What's the derivative of this? It becomes minus 4x to the minus 2. Okay. So then we could probably tidy that up there. I'd tidy that up to be minus 4 by minus 1. So that gives a plus 4 over x squared multiplied by sine 4 over x when you tidy it up a little bit. So then dy dx subbing into the product rule, which is u multiplied by dv dx, which is all this. I'll use a square bracket because it's quite messy. 4 over x squared times, maybe there's no need for a bracket there. If I do a bracket, I do it like this. Sine 4x, 4 over x, so just be neat. Goes off the square bracket, and then it's plus v, which I'll write like this, 4 over x, and then multiplied by a bracket like this with the 2x. Okay, what could we tidy up here? The x squareds cancel there. Just so you know, okay, don't be that student who thinks that this x can somehow multiply inside the cosine. You're in a really bad space if you think that kind of thing can happen, okay? You cannot get access to in there like that, okay? It doesn't work like that. So dy dx, so watch those trigonometry videos if you're a little bit confused about stuff like that. And again, this 4 cannot just enter in here, so it just has to sit out here. Okay, and then this is a plus 2x cosine 4 over x. Cool. All right, clear that away. Keep moving along. We're nearly there now. Yeah, so this we're not obviously doing this. We've already done our first principles question, but you're like, oh no, this is 2 brackets. So what you would just do here, you just multiply it out, and then you just do your first principles like I done earlier on the video. This multiplied out will give minus 10x plus 12x, so I'm getting a 2x and then a minus 20. Do your thing that I done earlier on the video on that with the x plus h, and that you'll be fine. Okay. Of course, the video's over an hour. Wow. Yeah, so I've got 2 things here that I want to do. Both of these. So let's do this. Obviously, pause the video, give it a go yourself. Get h dash x, the derivative of this. Okay, so let's do this. H dash x will be, the half does nothing. It's just going to be there at the end. The way you take a derivative of an ln is you go 1 over what's in there, and you multiply by the derivative of what's in there, so that'll be a number 2. Okay, and then the c is a constant, so the derivative of a constant is 0. So then this just becomes The 2 and a half would cancel. You just get yourself a 1 over 2x plus 3, like such. Now, you're told here the diagram below shows part of the graph of this thing here, 1 over 2x plus 3. You could graph that in Desmos if you want it. Confirm that's what it looks like. The shaded region on the diagram is between these graphs here, between this point A and 0. Okay, logical. This shaded region has an area of ln3. Ooh. Find the value of A. So if you want to get the area below a graph and the x-axis, you've got to use integration, okay? You want to integrate your function between these limits. So if I want to get that pink region there, that area in pink, that is equal to the integral from 0 out to where we're interested in the area, from 0 out to A, of whatever this function is called. So if this function was, 2x plus, I better not pick that one. But let's just say, this was, let's say this function was f of x equals e to the minus x. Well, then we would integrate e to the minus x. So you just integrate your function. It'll get you the area under the curve, and then you use your limits from 0 to A. It gets the area under the curve between the x-axis and those two x points, like it's shaded in there. But in this question here, the function is actually h dash x. So we're going to do the integral of h dash x. Now we know the h dash x's value. It's this thing up here. So area equals integral from 0 to A of 1 over 2x plus 3. But we cannot, there's no quotient rule kind of thing. So there's actually no way for us to integrate that on leaving cert maths, okay? But this is a part 2. The hint is that, okay, that is really just get the integral of h dash x. But sure, we know where h dash x came from. We know originally the integral of h dash x will go back to h of x, which we know. So hopefully people realize this, that this is actually, and it'll be a straight line now because we've done the integration from 0 to A. This will become a full h of x. And the full h of x is that thing there. It's a half ln 2x plus 3. Now you can add the plus c if you want, but when you've got integration limits like this, there's no need for a plus c, and I'll show you why in a second. Okay, so we'll get that area there in pink by subbing in the limits there. So we use 2 square brackets. First square bracket is when we put the a in. So this is a half ln 2 capital A plus 3. And then I'll put the plus c in. There's no need for it, but you'll see why in a sec. We go minus, we take away it with the other square bracket, putting in the lower limit. And then this will be a half ln 2 times 0, which is 0, and then that's just a 3. And it's plus c. Now, why is there no need for the c? Because look at this. You're going to get a plus c from this bracket and then a minus c from this bracket when the minus comes in. And so you see the c's were always going to cancel. So that's why when we do integration with limits like this, we don't mention the c after we integrate. So people would have just learnt that off by heart, but now you can see why. Okay, and as well too for area here, I can sub in ln3, which the examiner tells me to do. So then it's really just a game of algebra now. So I have that ln3 equals a half ln 2a plus 3, take away a half ln3. Okay, so that's a half ln3. You bring it over, it's plus a half ln3, and there's already an ln3 over here. So hopefully people can realize you get 3 over 2 ln3s then. From basic, and then you have a half ln 2a plus 3. Okay, you can hopefully see then that the 2's, you can multiply both sides by 2. So then you get 3 ln 3 equals ln 2a plus 3. Okay, what you do now is, there's a few ways you can solve this, but there's a smart way. You can actually bring the 3 back in and you put it on the power of this 3. So you should know that 3 ln 3 is actually ln 3 cubed. Okay, and the other side stays the same. And then ln 3 cubed is ln 27. Ln 2a plus 3. Now let's study this. That's ln something. This is ln something. Because there's an equal sign there, the insides have to be the same. So you can then separately write that 27 must be the same as 2a plus 3. So bring the 3 over. You get 24 equals 2a. And then a is 12. Really smart question that year. Okay, cool. What do you want me to get here? G dash E. Okay, so I'll take down G of X here and get G dash E. So we need to get G dash X first of all. Pause the video, give it a go, of course. Hopefully you realize that you actually need a product rule here. You need a product rule there. So you could probably go off and separately work that out if you want. You call that U and V. So you could say that U equals 3x, V equals ln x, du dx is 3, dv dx, derivative of ln x is 1 over x. And you sub those in, then you get 3x multiplied by dv dx, 1 over x. I'm not going to say something on the left here because it's going to just go in here. So normally I always say something on the left, but just here for the sake of it, I'm not going to say something on the left because I'm going to just put it in here, you know. So u times dv dx plus v times du dx, which is just a 3 ln x, and you can see the x's cancel here. So that really is just 3 plus 3 ln x. Okay, so g dash x then will be equal to the derivative of this thing, which we just worked out there is 3 plus 3 ln x. Derivative of minus 9x, which is just minus 9. Derivative of 4 ln x, well, the 4 does nothing. It'll just be there at the end. And then what's the derivative of ln x? It's 1 over x. And then derivative of minus 12 is 0, because it's a constant. So then this becomes 3 minus 9, so that's a minus 6 plus a 3 ln x plus a 4 over x. And then that's equal to your g dash x. And then we actually want g dash e. So g dash e would be equal to minus 6 plus 3 ln e plus 4 over e. We should know ln e, that's log ee, that's just 1. So then this is minus 6 plus the number 3 times 1 plus 4 over e. And so the answer then is equal to a plus 6 minus 6 plus 3 is a minus 3. So g dash e is equal to like 4 over e take away 3. Something like that will do. And then obviously you can give it to 2 decimal places, but that's actually neater. But you got to give it to 2 decimal places because they want it as 2. Okay. Right, cracking along. Hour and 9 minutes. Okay, we're nearly there. Given f of x is this, find the values of e. Okay, so we'll do what they're doing here. Okay, pause the video, give it a go, of course. F of x is equal to this thing. F dash x is equal to 0 when x is 2, find b. Okay, so you just kind of follow an instruction here. What you should probably do is square this out before to avoid needing to use a product rule. So I'm rewriting f of x here as x times x squared plus 2xb, multiply them together, double it, and then xb squared. You should all know how to square out a bracket. And so then this is x cubed. Good to always say what it is on the left. F of x is x cubed plus 2x squared b plus b squared x, you know. I probably should have put the b in front of that. It should be like 2bx squared, be neater, but it's fine. F dash x equals 3x squared, and then take the derivative of this, 4xb, and then take the derivative of this, it just leaves a b squared. We're told then that this thing is equal to 0 when x itself is 2. So you would just show it like this for the examiner. F dash, when you put 2 in, becomes 0, and then that's equal to 3 times 2 squared plus 4 times 2 times b plus b squared. And so then what we get is a, what's this? This is 12 plus 8b plus b squared equals 0. I've kind of switched the sides a bit here. Then you can factorize that. Obviously you rewrite it like this before you go factorizing it. Plus 12 equals 0. Well, that's a bit of an annoying thing to factorize, is it? Factor the 12. Oh, 6 and 2. 6 and 2, we're all right. So b plus 6, b plus 2. Find the values, plural. So there's 2 answers. B equals minus 6 and b equals minus 2. That's a minus. That doesn't look like a minus. So okay, and both of them are integers, negative whole numbers. Okay, Great. Lee got that out. What do I have here? Oh yeah, so this is what they call a composite function. This is where you put a function inside another function. So I have 3 stars here because it's pretty important you learn how to do this if you don't know already. So you're learning a bit of functions here, a bit of algebra, and then also practicing your differentiation. So pause the video, give this a go, of course. Right, so f of g of x, what that means is just like if you were getting f of 3, you would put 3 in for x, wouldn't you? So if you're getting f of g of x, you just put g of x in for x. And so what this looks like is ln 3 bracket squared plus 2. So you see how I've isolated where x was located? And in for that, you put an x plus 5. So basically you replace your x with whatever g of x's value was, x plus 5. So then I'll multiply this out a bit before I take a derivative. So that's why we always need to say what's on the left, because it's clear I haven't taken a derivative just yet. This is going to be ln, when I square this out, 3x squared, multiplying it together and double it, that's a 10x, so then it becomes a 30x. That squared is 25, so then it's 75, and then this is a plus a 2. So I'll actually put them together, save me a line. That's a 77. Right, so we got to take a derivative of that. So the way you take a derivative, it's easy. When you're taking a derivative of an ln like this, it's just as simple as 1 over whatever is in there. Simple as that. And you just multiply it by the derivative of what's in there. And the derivative of what's in there is a 6x plus a 30. And yeah, I'm not going to, oh look, it wants you to give your answer to 3 decimal places. So what you would write here, first of all, is 6x plus 30 on top over 3x squared plus 30x plus 77. And then they say put x in as a quarter to be annoying. So then you're just doing 6 times a quarter plus 30 over 3 times a quarter squared plus 30 times a quarter plus 77. To be honest, you'd get like 14 out of 15 marks for that. You get an extra bonus mark for showing the examiner you can smash a few numbers into a calculator, you know. That's the main answer there. And what's that equal to? That's equal to f dash g of x. Okay. Great. It's equal to the derivative of x when it's equal to the derivative of f when g of x is put in for its x value. Cool. Take a derivative of this. Now I think I've already done this kind of thing here, you know, where you just go u and you call that v. U is equal to x squared, v is equal to, you know, sine 3x plus 5. I don't think I need to do this, you know. du dx is 2x, and dv dx, the derivative of a sine becomes cos, the inside stays exactly the same. And then you just multiply by the derivative of what's in there, which is a number 3. And then you just sub them into the product rule. I can do it. You can see how quick this is. So you just go u times the other guy taking a derivative of, which is, bring the 3 out the front, 3x plus 5, and then add it to v, which is this thing, multiplied by du dx, and I'll just write a 2x out the front, and it's done. Okay, cool. See how quick that was. See, can you do that quick? Okay, yeah, so this, we've already done one like this earlier on. I'll do it again because they're pretty important. Okay, so pause the video, see if you learned from when I taught you these before, either in this part of the video or in the previous part. These are pretty important because they're pretty much due to come up soon on a state exam. They've been based on mock papers, but for some reason the state hasn't asked one of these in a thing. Okay, so hopefully you remember the way to do this is to call it y if they haven't already. And then you got to state, you got to make a substitution that you're going to say u will be equal to 2 over x squared. So then your y becomes cos inverse u. What you're actually looking for is the derivative of the red thing, and the derivative of that will be called dy dx. We get our derivative of that by pulling it apart, and dy has to go there, dx has to go here. We can put whatever we want up here, so we can go du and du. Because they're the same thing, we could just cancel them down, and then you get back to dy dx. That should make sense to people. Again, revise the rates of change questions and the chain rule questions in your book if that doesn't make sense. So we get our answer, dy dx, by getting these two things separately and multiplying them together. Where do we get dy du? We get dy du by getting the derivative of cos inverse u over 1. And I think you remember that from the tables book before. I better get it up here. So you go down here and you see that cos inverse u over 1, x is u here, 1 is a, it's minus 1 over the square root of 1 squared minus u squared. Okay, so that will be equal to minus 1 over square root of 1 minus u squared. And then du dx, obviously we'd rewrite u as 2x to the minus 2 before we take a derivative. Du dx, that's why it's so important to say what's on the left so we keep track of what everything is. Du dx is equal to multiply down by the power minus 4 reduce the power by 1 like such, and then you just sub in here. So then dy dx equals dy du, which is this thing, minus 1 over square root 1 minus u squared, times du dx, which is this thing, minus 4 over x cubed when you bring it down the bottom. And you don't leave it like that, you sub back in whatever your u was. Dy dx equals, they'll become a plus 4 on top over, no need to say plus, over the x cubed can come out the front here. And you have a square root, and then the whole point of this is to swap the u out with what it originally was here. And u was 2 over x squared. And then we put a squared there because it's u squared. And that's full marks. Cool. So one of these. If one of these come up, you just kind of follow the instructions. So give a go there. Pause the video and give that one a go. Okay, so what you do here is you actually go and work out dy dx, okay? Now dy dx is a little tricky here because you actually got to use a product rule, hopefully you realized. So u equals x to the 4, v equals e to the 3x. Underneath it you write du dx, 4x cubed, and underneath this you write dv dx, which is really straightforward, stays the same, multiply by the derivative of the power, 3. So that's really 3e to the 3x. Right, so then what's dy dx? Using our product rule, it's u multiplied by dv dx, which is 3e to the 3x, added to v multiplied by this thing. So that would be 4x cubed e to the 3x when you multiply those together. Okay, so I can tidy this up. This here is 3x to the 4 e to the 3x plus 4x to the 3 e to the 3x, right? That is dy dx, right? So you just follow the instructions up here, check if this formula works. This is one of the rare things where like you're asked to show something, but what you actually do is you use the thing you're meant to show by subbing into it. So in for dy dx, I'm going to put this. State for the examiner though what you're subbing into. So dy dx minus 3y equals 4y over x. So then putting in, let me get a good color for this, I'll use purple. So in for this first guy, we're putting what we worked it out to be, down there in red, plus 4x to the 3, e to the 3x. Take away 3 times y. What's y? Y was this original thing up here, x to the 4, e to the 3x. And we're checking if that's equal to 4 times y over x. So hopefully you can realize that that's going to be 4 x to the 3 e to the 3x. Why is it x to the 3? Because you have an x to the 4 on top and an x on the bottom. Straightforward stuff. So let's multiply this out and take it away. So you can see hopefully that we've got 3 of them there and we're taking away 3 of them here. So they cancel. And then you're left with 4x to the 3 e to the 3x there. And then that's supposedly equal to 4x 3 to 3x. Oh, but they're the same thing, so then it's true. Left equals right. What you could do is you could say LHS, left-hand side, equals RHS there if you want. Okay, tick. It's a good question there. They could come up, you know, got to be prepared. Uh, will I do this one? It's just another product rule, isn't it? U is that, V is that. I better do it. Pause the video, give it a go, of course. U equals X, V equals sine. We write it like this. X to the minus 1. Du, that looks like a Y. Du, dx will be the number 1, derivative of that. dv, dx will be equal to sine becomes cos. The inside stays exactly the same. And then we multiply by the derivative of the inside, which will be minus 1 out the front, x to the minus 2 like that. So then we sub into our product root formula, dy dx equals u, multiplied by dv dx, which is this thing. I'll tidy it up. This will be like a minus 1 over x squared out the front. So it's really minus cos 1 over x in here, because that's what cos minus 1 is, all over an x squared. And then it's a plus v times du dx, so that's nice and simple. It's just sine 1 over x. Okay, and then what tidies up here, the x will cancel there with the squared on the bottom, and so you'll really just be left with dy dx equals minus cosine 1 over x all over x, and then plus sine 1 over x. And as I said earlier, that x can in no way go in and bother what's inside the trig thing there. Okay, that's fine. Kind of worth doing that, I suppose, to show students how to tidy that up and whatnot. Oh, so there's another part to this. So I need the derivative in pink probably to do this. So that's the derivative there. That's the formula for dy dx, and we should all know what is dy dx. dy dx is the slope. In one word, it's the slope, and in many words, it's the slope of the tangent to the curve. That statement there is a statement for what dy dx is. And we're asked to find the slope of the tangent to the curve when this is the value. So that basically just means put in, to get your slope, you just put in 4 over pi for x. Now, if x is 4 over pi, 1 over x is pi over 4. So this becomes cos pi over 4 all over 4 over pi plus sine, again, it gets flipped, so it becomes pi over 4, like such. And then the rule is the bottom will come up here. You could just multiply above and below by pi if you don't see that. So you get minus pi cosine. We should know what this actually is here. You can type that in your calculator when you're in radian mode, but I believe that's the 1 over root 2 thing. So that then is 1 over root 2, or it'll say root 2 over 2 in your calculator. And then there's a 4 on the bottom here, because the 4 stays there, the pi comes up. And then this here is the same thing, it's 1 over root 2. So if you wanted to tidy this up in neat algebra, the slope, you could factor out the 1 over root 2. Again, you don't necessarily have to do this, so then there's a plus 1 left behind there. It's taking the 1 over root 2 out, it leaves a minus pi over 4 here. Is it 4 there? Yeah, so that wouldn't be a 2 then, it'd be a 4. That'd be a 4, and then this is a plus 1 here. And then you could just type that in your calculator, but sometimes they could make a tougher question and they want you to present your final answer like that. So better you see me do that than just seeing me type things into your calculator and write decimals on the page. Ugh, it's more. Okay, so this is an important question. I think we already done one like this in the part 1. So pause the video and make sure you're able to do this. So we're nearly there. This video is on, what's it now? Nearly an hour and a half. So, right, first of all, we'll do what they instruct us to do here, which is work out f dash x. That's an exponential. The derivative of an exponential stays exactly the same. And then we multiply by the derivative of what was in there, in the power. The derivative of cos x is minus sine x. So f dash x here equals minus sine x e cos x. And you bring it out the front. Hence or otherwise, it's obviously hence, we can't do this any other way. We need to use this from up here, work this out. Right, so how do we do that? So the idea is here is to rewrite f dash x as dy dx. dy dx equals minus sine x e cos x. What we do then is we multiply across by the dx, leaving dy over here, and then we got minus. These are tricky questions, you know, but they can come up. And then this is all multiplied by dx. What we can do then is we can integrate both sides of the function, of the equation, sorry. When you integrate the left side here, it becomes y. When you integrate this, see how it looks very similar to what we have up here. You can actually bring the minus outside of an integral. That's something you should know. If you don't know that, revise your integration. Sine x e cos x dx. So the thing we're actually looking for here, now when you integrate both sides like that, you do need to put a plus c in. You do need to put a plus c in, but because we've got limits here, we can just put between 0 and pi over 2, and same here, this thing will be between 0 and pi over 2. So that looks a bit complicated there, you know. Don't be too panicked by that. So the idea is here, the thing we're looking for is this thing here. Study it carefully. That is the thing there. Yeah, that's her there. So basically, this is minus it, so we can just multiply both sides by a -1, and so we get that the pink thing on its own, which is what we're after, integral going from this to this, of sine x e cosine x dx is equal to minus straight line 0 pi over 2 y. And we know what y is. We can just put the y in. Y is e to the x. So again, there's going to be a good few of these in your textbook you can practice, you know, and you can get good at them. So then this is equal to straight line 0 pi over 2, and in for y then we put e cosine x. And now we'll evaluate it, and we use two square brackets. Now we got to be careful here because there's a minus, you know, so we say equals, so we'll do a big minus on the outside, and then we'll have our two square brackets on the inside. So first of all, we put in the pi over 2 in for x, so that's e cos pi over 2. Close off the square bracket, then it's minus with the lower limit in the 0, so it'll be e cos 0. And be careful, cos 0 is actually 1. Okay, and that's going to be the answer to this question. Again, you want to maybe have this over here. So in the final thing, because that's what's on the left there, it's this thing. So for my final answer, this integrated from this to this, okay, is equal to this here. Now, cos pi over 2 is 0. So then that's minus on the outside. First bracket gives a 0. Minus this bracket. Oh, sorry. That there is a 0, but it's e to the 0. So then that's 1. Okay. That's a 1. You could type it in your character editors. It would do that for you, you know. Cos of 90 is 0. And then it's e to the 0, which is 1. And then this cos 0, that's a 1. So then this is just e to the 1. And so the overall answer here will be minus, so it'll be e minus 1 will be your answer. Okay. As I said, they are tough. They are tough, but you can kind of practice them in your book. And like, you don't have to be like, you'll still get pretty much full marks if you're not as accurate with when to put the straight line in and how to do it. But you can definitely jig it, you know. Grand. I'll clear that away and get set up for the next question. Okay, we're back. So hopefully there's not too many more questions. We'll be able to finish the video. It's looking good. Oh yeah. So this is a bit of a funny one here. This is a sample paper. So these are like, the wording of these are a bit unusual. They're like 12 years ago kind of thing. So it just says write down 3 distinct antiderivatives of this. So that's like integration, antiderivatives or integration. So one distinct one would be like x to the 4 over 4 minus 3x cubed over 3. You're just integrating it. And then you're just, instead of going plus c, you're just going like plus 1. You write the same part there, and then you go plus 2. So basically you're just making up your own c because they're distinct possibility. And that's what it means here. What does it mean by indefinite integral? It's basically it's the integral with a plus c. That's, you know, it's a stupid question, this. Explain what's meant. It's basically there's an unknown c that we need an initial condition to work out. So then it's like write down the indefinite integral of g. So it's this x to the 4 over 4 minus, that becomes x cubed plus 3x plus c. Okay, cool. X, ln x, take the derivative, and then, yeah, so this is similar to what we had before. So we don't know how to get the integral of ln x. I don't think it's in the tables book, but we can do it by following this instruction. So this is just like that complicated one I done a second ago with the cosine, the sign that had the x in front of it, the complicated one. Anyways, you just follow the instructions here. You got a h dash x, you got to use a u and a v here. U equals x, v equals ln x, du, dx is 1, dv, dx is 1 over x. The derivative of ln x is 1 over x. Okay, so then you sub those in to the chain rule, or sorry, not the chain rule, the product rule, and it's u multiplied by dv dx, which is 1 over x. And then it's plus v times this du dx, which is ln x, because 1 times ln x is ln x. So then this is really x times 1 over x is 1, so this is just 1 plus ln x is h dash x. Okay, so then it's like work out the integral of this. So this is like what we've done before. So what you'll do is you'll call this dy dx, okay, dy dx, and say it's equal to 1 plus ln x. You then multiply across by the dx like we've been doing before, and you get dy equals 1 plus ln x multiplied by dx. You can then integrate both sides like such. And now the integral of this side becomes y, and the integral of this side, well, what does it become? This is two parts, so we can just do each part separately. What's the integral of 1 with respect to dx? That's a full x, isn't it? And then we're left with this thing that we don't know how to do, which is the integral of ln x dx. You can put a plus c here if you want, okay, or we can add the c at the end, all right? So, yeah. So then what does this equal? This is the thing we're actually after. So what we'll do is we get the thing we're after. Look, this is what the whole question's about here. We get the pink thing on its own. So I'll go for maybe black color here. The integral of ln x dx on its own is y minus x. And so then what's y? Well, we know y from up here. It's x ln x, subbing in for y, and then this is minus x. And because this question didn't have any limits, you'd lose a mark if you didn't write plus c. But to be honest, don't be too panicked about the c. If you forget it, you lose a mark or two. What's more important is you understand what's going on here, where you multiply across by the dx, you integrate both sides, the integral of dy becomes a full y, and then you kind of, when you integrate both sides, the thing you're looking for will appear, and then get everything away from it. And so this was an easy enough one here. And then you'll usually be subbing back in the y that you had from before, And then it went. Okay, cool. So they're actually quite easier here where you don't have the limits, They're easier right out. Good, good, good. So differentiate this with respect to x. Yeah, so that's an interesting looking one here. Okay, so pause the video, give that a go, everyone. Okay, so let's call it y. And then anything to the power of a square root is the same as being to the power of a half. You should all know that. Plus x minus 2. And the way you take a derivative of this is you multiply down by the power. You keep the inside exactly the same. You reduce the power by 1. Take 1 away from a half, you get minus a half. And then you multiply by the derivative of the inside, which is 6x plus 5. And then you can tidy this up. When you have a minus a half, it's the same as a square. It's the same as a plus a half power on the bottom, and so that's the same as. I'll actually do this step by step for you. So there's a 6x plus 5 on top. There's the half, so that means there's a 2 down here, and you can bring this underneath, and it's a 3x squared plus 5x minus 2 to the power of a half. But anything to the power of a half is the same as a square root. So you could then write this as that, and that is the neatest way you can give that answer. That's a 2. Okay, hope people are happy with that. It's a cool question. Very exam grade stuff. And I think I'm on to my last question. Okay, so great. This is, oh, there's something else here. Okay, so let's try and look at this. So this is like that graph thing I had up before. Let me get it up again so people can see it. So let me pause this here. Okay, so this question is all to do with this graph thing. So I've already explained this here on how the points of inflection dashes down to where the linear crosses this, the second derivative, and then how the turning points cross down to where the roots are of the quadratic when you're dealing with the cubic being derivative. Okay, so this will help when you're studying this here. So this is a really good question. This is something like this is due to come up again because this was a really well designed question. So pause the video and give a go at this, of course. Okay, so let's do this. So what we've got here is a trigonometric function, right? This is sine, by the way. We should know that that's sine if you've watched the trigonometry videos, okay? So the derivative of sine is cosine, and then this is a cosine here. But you didn't need to know that either. You just know that, oh, the trig, when you take a derivative, it becomes another trig function. And so when you take a derivative of cos again, it becomes minus sine. And you should know if you've watched the trig videos, minus sine looks like that. It's basically normal sine flipped in the x-axis. So that is how you do that. So basically, G is what you were called. G, you become capital A, and then you become 3. Okay. So then what do we have? There's a quadratic, a U-shaped quadratic. When you take the derivative, this will be its turning point here. So when you take a derivative of that, it will become a linear, and the linear will cross the x-axis at that point there. Oh, look at it doing it here. So then this is K, its derivative is B, and we should all know that when you take the derivative of a linear, like say that was 3x minus 7, right? When you take the derivative of this, it just becomes the number 3. So then like dy dx here would be just equal to 3. And if you graph that, it's just a horizontal line that goes through 3. And so that's why the derivative of b is I. Okay. If you don't believe me, just graph like y equals 3 in Desmos. You'll see it's a horizontal line. Okay. So now the cubic, the one that lines up with what we were talking about there, the cubic has 2 turning points here. So then they will be where its derivative will be a quadratic, and that quadratic will have roots at these locations here. And look at them. So then that's D. That's D, and you're called F. And then remember, it has like a point of inflection here. So this is where its linear will cross the x-axis. So that's that there. Okay. And the same thing, it's like the turning point for this here. Okay, so then that's part 2. And then sure, you could just use a process of elimination if you don't understand the exponential ones. So this is obviously exponential decay, isn't it? So it's h. What this looks like here looks like something like y equals, say, we'll call it like 2 to the minus x, something like that, right? So then if you take a derivative of this, if y equals 2 to the minus x, what does d... I'll actually make it easier. Oh, no, that should work. Yeah. So, oh no, you should be careful here. Just careful. I'm going to call that e. But there's a good homework thing there. You use your formula tables if you did want to get the derivative of this. It has something like an ln2 in it, so you can go to your tables book there and just see the thing here. It would have been like 2 to the minus x with the minus 2 and probably a negative out the front from the chain rule. So that's a good homework one to practice there for people, what the derivative of that is, you know. Great, but I'll make life easy and make it an e. And so then the derivative of this is basically, it stays the exact same, but then you multiply by the derivative of what's in the power, and then that's a minus 1. So what you can see here is, look carefully. The derivative is basically the original function just with a minus out the front. And we should know that when you put a minus in front of a y like this, it mirrors the original function through the x-axis. So that's why C looks the way it looks. See? It's mirrored. It's the very original function mirrored through the x-axis. Okay. And so look, think about it again. You take another derivative of this. You go and you get d2y dx squared. The minus out the front does nothing. It's like a minus 1. So it'll stay the same. And then you multiply by the derivative power, which is another minus 1. It goes back to being e to the x. And that's why it goes back to being its original function like it was up there. Because that mirrors it again. But the better way to think of it, it's just its original function. So that's why it becomes IV. And yeah, I basically explained why all of them become who they become. And so it just makes you explain one of the rows here, but I explained them all to you verbally there, okay? So I think that's us. Of course, there's one final question just to finish it all off. It's an easy one though. Um, Pause the video and give that a go. I'm going to hammer it out here. F dash x will be equal to, it stays the exact same. That's a nicer way to write a half x squared. X squared over 2 is a nicer way to write it. And then you multiply by the derivative of the power. You multiply by the derivative of that power, it becomes minus 2x over 2. So it's a minus 2x. Now the annoying thing is here, to get another derivative of this, you have to use a product rule. So u equals e to the minus x squared over 2. V equals minus 2x. Du dx equals, stays the exact same. And then you just multiply by a minus 2x like we did before. Actually, no, it's not. Where am I getting this minus 2x from? You multiply down by the power, and then there's already a 2 there, so it's just going to give minus x's. My bad. Let me confirm that. So it's the exact same, and you multiply down, you take derivative power. So that's minus 2x over 2. Yes, it's minus x. So then this here is really just minus x. Same thing here. This is just minus x. Yep. And then dv dx, derivative of minus x is minus 1. Okay, so then you sub them in here. The derivative will be u minus x squared over 2. Multiply by dv dx, which is just minus 1, plus v, which is minus x, multiplied by du dx, which is this complicated expression here, minus x e to the minus x squared over 2. What does this become then? It becomes minus e minus x squared over 2 minus, oh, it'll turn to a plus x squared e to the minus x squared over 2. So you see both of them have an e to the x squared, e to the minus x squared over 2, so you can factor that out. E to the minus x squared over 2. You factor that out, it leaves a minus 1 there and a plus x squared here. And sure, that is x squared minus 1 there. It is done. This video is over. Okay, so that covers that entire study clicks document. Okay, so you've definitely learned a lot of stuff there from that part 1 and part 2. So if that helps you, leave a comment saying it helped, and subscribe, of course, for more videos. Thanks for watching. Be sure to like too.